Do we have like the whole board? I like how the stand here blocks.
All right, ready for video?
Yeah, I'm ready. Are we good? The microphone is like green? Okay, okay. All right, thanks for coming, guys. I'm going to be talking about like computer architecture, as you know. We're going to be talking about like just the basics and fundamentals of like what is programming. I know like half of you guys already know, but like we'll just talk about it, you know, for fun. What else are we going to do in the summer? Have fun? No, no, that's not a choice. That's not a choice. So the first thing I want to talk about is like programming, like from the perspective of like of a first year, right? So when you first learn how to program, the first thing that you learn is like the prof will sit down and be like, okay, so like what we're going to do is we're going to print. And like that means nothing to most people, because like what is print, what is happening? You see text appear on the screen when the professor writes down the word print, hello, and the hello appears somewhere for some reason, you know why. So the first thing that we have to understand is that we are trying to actually make a computer do something. But what is that something? And so the first thing that we do is we hit our keyboard keys, and then text appears on the screen like magic. But does anyone know what text actually is? Like, actually. Yeah, like you could take the ASCII representation. So like you could say like, oh, this chalk is great. Oh, that's awesome. Maybe it's the board. Is that even legible for you guys? Okay, we'll just keep going with it then. So like the ASCII representation is like the classical representation of text. Yeah. Yeah, we'll just keep going. So ASCII is like the classical representation of text that we use, but it's a little outdated actually. And so most professors will tell you that we use the ASCII representation, but that's a lie. And so we'll go through the ASCII representation. It's very simple. You just put characters in an array, right? Or in a list, or in a sequential container. It doesn't matter what it is. Now, does anyone know what a character is? Very simple, right? You are right in some representations that we'll talk about, but it's 1 byte in ASCII. Now, 1 byte is, we're talking about 8 bits of data, and this 8 bits is just the representation on the hardware. But what we're actually talking about is we're talking about a number. And so we're giving a number a meaning, right? So what's actually happening here is we're not putting the letter A in an array, we're putting a number in an array. And then what we're saying is that we believe that this number is actually a character, and so we're going to use it to figure out what to display to the screen, right? So we're not storing a character, we're storing a number, and we're praying that that number actually means something. And so we just say that it has a meaning. Now this is outdated for the reason that if you wanted to represent other text forms, like let's say you wanted to write like Arabic or Chinese, or one of the Chinese scripts, then you'd run out of space because these 8 bits give you 2 to the 8 different possibilities, which is just going to be 256, which is way less than the amount that you actually wanted to represent. Because, well, I mean, Chinese has like hundreds of thousands of like symbols that you can represent, so you're not going to actually try to represent that inside of 256. So what we're going to do is we're actually going to expand out our data. And so one of the, like probably the most universal format that we have is the Unicode format. So we have Unicode. Oh, God. Unicode is a format where we take the idea of numbers and we map them onto meanings. They don't have to actually be visual meanings. Like we can have control characters just like ASCII, where you have like new lines, you have like null terminators. In Unicode, you can have some like weird things like you can have the letter I, and then you can also have the idea of remove the dot on the I, right? And so some languages don't have a dot on the I. In some, like that actually has a meaning. I believe Turkish is the one with missing I, or like missing dot means something else different. And so each of these numbers in here are what we call code points. So we have code points. And then what we'll have is the actual representation of these things in a visual sense. If you take this entire block here, then that's going to be a glyph, right? If you actually print it to the screen, it's going to be a glyph. But these two separately are not actually going to be visual. And so this happens a lot, and Unicode is like a nightmare because language is a nightmare. And so if you wanted to go through this, you'd have to go through like, oh, Arabic has like right to left, and how are you going to read that? And you have merging schemas, like Arabic is a nightmare. I hate Arabic now. But when you actually go to read text, there are going to be multiple different representations of Unicode too. So I'm sure some of you have seen the idea that Unicode is represented in the format of UTF-8, UTF-16, and UTF-32. So this is why you'd be right. UTF-32 is 4 bytes, and so that's correct. But these ones, these UTF-8 and UTF-16 have these control bits that allow you to find out if you have another byte. So for example, you'll have something like 1, 0, and then some nonsense here. And that would mean that you would have to read another block in, right? And you'd have more data. And eventually, you'd use these sections of data. Like, let's say this whole number is the next section. There's no control part. You'd merge those two together, and you'd produce something in the format of UTF-32. And so UTF-8 will take up more bytes if all of your characters or code points wind up being longer. But generally, it won't be. And then the other thing about UTF-8 is this section right here maps to the like the bottom half of ASCII. So if you want to keep representation on like your terminal or something like that, you'll find UTF-8 is the most useful for you, just because if you print out UTF-8 and it happens to be all English characters or whatever, then it will just print out as if it was just normal ASCII, and it would work out because the numbers are actually the same. Yeah. So this is like the general representation of text that we use. And I've seen this mistake happen a lot, where you assume that you're using ASCII because your professor has only told you that ASCII exists and that's the only thing in the world. Don't make that mistake. Actually read what your format that you're given is. And that applies to most situations. You assume that you're working with some format, and then it turns out you're not. Some people have assumed that you have little endian format. Little endian format is a format where you have your bytes leading up on the little side is on the far side, right? And so we'll have little endian over here and big endian over here, where, sorry, that's like dumb, but like you can have flipped representations of your bytes. So if you have 4 bytes, you can have them in reverse or not. And I see this often, especially in the networking field. When you first enter, you assume that the number that you printed, like the number that you print out, is going to be in the same format that your computer uses. Turns out it's not, and then you, I don't know, you leave computer science, and you give up. But do we have any questions about text before we like move into like actual computer stuff? No, no questions. That's awesome. I didn't want to answer anything about text anymore. I'm just going to erase this. So next thing is that like when you type on your keyboard, you produce text. That's cool. It appears in memory somehow in whatever format that whoever decided. Doesn't really matter. The text appears and it's stored in memory. But then the next thing that we need to be able to do is we need to say, okay, well, I have text now, but if I have just a little bit of understanding about what a computer has, the computer doesn't know what the text does, right? If I write if I write print into my text file and I save it and I say I want to run it, what does that mean? Like, what does the computer do when it tries to do that? And so we have to understand what we're targeting first. And so let's say we're targeting like one of the machines in the room. The majority of them will be running something called x86 or many names. I'll give you all the names. So we're going to go with Intel architecture 32. We could talk about, let me get the eraser. You could talk about the x86 architecture, and you could talk about AMD 64. You'll see this like hellscape of a naming scheme. These are all the same. No one knows why we did this to ourselves. I really don't understand why we did this, but it doesn't matter. You also have IA 64. You'll never see this. This is the Itanium instruction set, and it just doesn't exist. You'll see things like ARM. ARM runs, a lot of your phones and MacBooks will run ARM, or embedded systems like the router like outside that's running this, the Wi-Fi for us. And then you'll see other things like RISC 5 or MIPS. These are all just names of architectures that our computers can run. So there's different like formats that our computers can actually run. There's specifications for numbers that your computer will read in and then use its meaning to actually produce some change inside of its circuitry, right? And then it's going to do something hopefully useful or maybe not. And generally, people often talk about the differences between this one and literally everything else here. And they go, this is CISC and this is RISC. I hate that because there are different ways that you can categorize something as RISC or CISC. So CISC is complex instruction set, like computer, I think, or something. Doesn't matter about the last C. And then RISC is reduced instruction set. Now, what does reduced mean and what does complex mean? Honestly, no one agrees. But some people think that RISC means you have load store architecture. So when you go and access memory, you will load things and you will store things explicitly. Or maybe you could pack that data directly into your operators, and then your operators will do it like kind of implicitly. And so you could consider that to be RISC versus CISC. Or maybe you could consider, instead of addressing memory, you could talk about how many instructions do you have. You could talk about whether or not you have variable length instructions. And there's honestly too many things you could talk about. So I don't like the distinction between RISC and CISC being so like binary. Instead, you should think about it as this. This architecture here has variable length instructions, just like UTF-8 that I drew earlier. And then the RISC instructions, some of them, you can't really consider ARM fully because ARM actually has multiple instruction set types. If you think about Thumb2, the subset of ARM in Thumb2, you have 16-bit and 32-bit sets, which are two different instruction lengths, which is variable length. So you have to really look at what you are actually targeting to actually understand it, and instead of just yelling the word RISC versus CISC. But these are instructions, just like kind of how those numbers are instructions for the computer to print things out. And so we have to target these instructions. But to understand what are these instructions, you have to understand kind of what the basis of all of these computers do. I do feel like most of you guys kind of know, but we can talk about the basics. So we have something called the move operator, and we have something, how's the cable? Cool. And then we have the middle board. Yeah, okay. So we have the move operator, very classical one. I'm going to be using x86 for all of this because I don't know these other architectures as well, but just pretend. So the move operation allows you to move between two variables in your computer. So your computer has variables in there. We'll call them registers. And you can move between the registers. Move means copy, basically. And so we'll copy registers between each other. We can copy from memory into a register or from a register to memory in the x86 land. So you could do something like you could copy memory like that, and then into a register 1, for example, right? And then you could say something like, I don't know, we could add. So that's another thing that we'll do. A lot of math operators will exist inside of this land where you can just do something, add things together, divide, multiply, all the basic math stuff. Something cool to note is that divide is a nightmare on the computer, and so you probably shouldn't try. If you want to keep your computer performance high, you probably don't want to be dividing, like ever, just never. You could add this register to itself and then store it inside of itself in the x86 architecture. Doesn't really matter. You could do something like a jump, okay? You could jump from something to some location. So I could say, let's say this location is 0. I could jump to position 0, for example, right? And these are like the basics of the things that you can do. You can do things like compare. You can do all sorts of things. All the stuff that you've been programming in, it really looks the same as this. So it's nothing too crazy. And so we're just going to like, we all get this, right? Cool. So our goal is to target that from text. And so basically we have to create this translation system, right? So first of all, you understand that computers take in this as binary. This is our human representation of it. It's nothing like the actual binary because the binary is just numbers. The computer will take in the numbers and it will translate it into its format that it needs, and it'll do something with it. And we'll talk about that in a second, well, in a while. But to actually get here, we're also going to translate. So we're basically going to do the same type of work that CPU designers generally do, except on a higher level. And so what we'll do is we'll take some text. Let's say you have something like, you have some text that says we have an integer x, and it's equal to 32, okay? And I'm going to put a semicolon because I write in C. And then I'm going to say if, let's just stand on this side for you. If the x is equal to 2, we can say something like x plus damn it. We'll just go with equals. X equals x plus 2. And then we'll say else x equals x times 2. Is there anything else I wanted here? Not really. This is fine. So the first thing that we want to be able to do is we want to be able to understand what our text is, because in memory, this is just numbers. We just have numbers. So the first thing we have to be able to do is we actually have to break down these numbers into something that has more meaning, right? Because we want to be able to say, okay, like I have some text, but I have no idea what this means. Let's figure out what it means. So the first thing is we're going to get each character in here, right? Each piece of relevant information, each set of semantic information, and we'll break it down, right? So we'll get each character. I'm not going to draw me getting each character. That's boring. But then the next step is we're going to get each big, large piece of semantic information, and we're going to break that down as well. And this is the part where we say, okay, we have something meaningful to the program, right? There's the first piece of meaningful information. We call it a token, the base piece of information. You can also call it a lexeme, but I don't. So we'll say integer, obviously something that seems like its own piece of information. We'll say x. We won't take any white space because C does not really care about white space. And then we'll take this equal sign, the 32, semicolon. Maybe you'll take the semicolon. This is an optional thing depending on how you're doing this. And then you'll take this, and I'm just going to box everything up for you guys so that we can have something to talk about. Yeah, that's gone. It's very emotionally painful sitting here. Okay. Okay. So it looks terrible, but we have this stream, and I've ignored white space, and this is just going to become, well, most of the time compilers these days will not really create the whole array of all the tokens that you're going to have, because that's going to take up way too much memory, because you're just going to duplicate your entire structure again. So you'll normally do this one part at a time while you do the next step. But this first step that we do is called tokenization. And after we tokenize, we're going to do a thing called parsing. Parsing can be done in like 100 different ways. One of the ways is just standardly, we just throw them into this thing called an abstract syntax tree. It's a tree that represents the ordering semantics of each thing in this file, right? The other ways we can do this is we could do something like, we could try to push it into something called like reverse Polish notation, where you push operands in. So you could push like this 32, or you could push this x in first. You could say create the x and then push 32 into the x and so on and so forth. It's a lot more involved, and you have to understand a lot more about your language to do that. The easiest way to do it, which isn't especially efficient, is the AST way, but it's like the easiest way and it's the most flexible way, and we'll do it the most often. So we'll say something like, do I really want to do this? I'll do it. We'll say x is equal to 32, and we'll tag it with the idea that it's an integer. And then we'll say, okay, the next step, because the tree can actually have branches, I'm not going to draw each thing if it doesn't actually have a branch in a different direction, so we're just going to draw it linearly. But the next thing actually does have a branch, so we'll say, we're going to say if x equals 2, then we branch, and we'll have a true, and we'll have a false. If you didn't have an else, you could maybe format your syntax tree in a different way, but we do have an else, so we'll handle that. In our true case, we'll just say that we'll create an x. We'll just set x equal to x plus 2, and then we'll just say x is equal to x times 2. And then we need to be able to merge these two. So I'll just say this is its own block. It's its own node. And then we'll say anything that comes after is an instruction that we'll put in there. That way we can actually merge these two at the end. So that's the next thing that we have. We have an AST, right? So we have our tokens, our AST. And then the next step is that we need to actually get closer to the hardware, right? Because now we know what our program kind of looks like. We need to get closer to the hardware. But there's also another step that we'll often do, optimization. We all kind of know compilers will optimize code for us, and they'll make our life a lot easier because you don't have to think as hard about like, how do I make this code run well and also do the thing that I want to do. You can just have it go, and then hopefully the dumb things that you write will actually become not dumb. So I'm going to erase this pseudo assembly here because this is kind of useless. We're going to make room for the next step. And this next step, I'm going to use the classic form of translation that we do in imperative languages. I know a lot of non-imperative languages will use a different form. I can tell you them, they're called ANF and CPS, call passing style, and administrative normal form. Doesn't matter. We're going to use SSA. SSA is single static assignment. It just means every variable that you want to mutate, you don't mutate the variable, you actually just create a new variable. And this is very similar to actually how the hardware works, and you'll see that very soon. But we don't actually want to mutate here because we can do a couple optimizations. If you never mutate your code, that means if you have a constant, you can replace all of the cases where you have that constant or that variable with that constant. It's called constant propagation. And then you can also then start folding constant expressions and stuff like that. Very common optimization, very simple. And doing that is a lot easier if you don't have mutation. So we'll have single static assignment. And so we'll say something like x1 is equal to 32, and I'll put it that. And then we'll say, in this format, we'll say, okay, well, we need to be able to do two things at once. So we don't really know how to do that. So we'll do something similar to the assembly style, where we'll just jump to the one that we want. So we'll say something like, if x equals 2, some people save this into a variable itself. I'm not going to do it to save space. And then we'll just jump. We'll jump to like, we'll call it label 1. And then we'll put label 1 here. And then we'll say, okay, so if it's true, we want to jump to that label. So we'll say this part goes in here, and we'll just say x. We'll say x2, and this is a 1, sorry. X2 is going to be equal to x1 plus 2. Some people will save that 2 into to a variable as well. I won't. And then we'll say something like, we need to merge this x2 with the x1 after, because we're going to potentially use it. If you weren't going to use it, then it would turn out that all of this code would be useless and you'd delete it all. That's called dead code analysis. But let's just pretend that we're using x later. And we'll say we'll merge x2 with x1, or sorry, x1 modified, right? So we'll modify x1 with x2. And so we're just stating to our language, hey, we're going to modify x1, but we don't in both branches or in one branch. And so we need to be able to merge it later. And so you're going to keep some sort of table that says, oh, I'm going to merge this. And then you're going to say, okay, so otherwise, if it's not true, then you're going to say we're going to run this. So we're going to do the exact same thing. You can say x3 is equal to x1 times 2. And then you'll merge x3 with x1 modified. And then at the very end here, oh, I'm missing a part. We'll just put it here. We're going to jump to L2 here, and we're going to put L2 here. Hopefully that's legible. This just means we want to skip this section here if we actually ran the false case. So we don't really want to run both. So we're just skipping it. And we'll say L2 is here. And then any of our code that we would write here would appear. And this looks basically like assembly, but we have a couple features, like we're kind of simulating registers, but we are kind of saying we have like infinite of them. And as you know, your computer is not infinitely large. So we're just pretending that we have infinite space. A couple things that we can do here are, first of all, you can see this is a constant. So you can just propagate this constant throughout all of your code. The second thing you can see is this is now a constant expression. So you can merge that and you can realize that this jump will never happen. So you can remove this dead code, and you can just run this code right here. You can notice that this is a multiply. You can do something called a strength reduction. It's a peephole optimization. A peephole optimization is where you take a window and you just say optimize within that window using pattern matching. And the pattern says if you're multiplying by a power of 2, just shift it to the left by n. And if you know how binary kind of works, like just like decimal, if you shifted your decimal to the left by 2, you'd multiply by 10. Same thing for binary. It's base 2, you'll move it by 2. So we'll do a shift left because why? Because the shift left is actually a faster operation than a multiply. Multiply typically takes a lot longer because you have to have a larger circuitry to actually be able to multiply. But in this case, we just know we're just going to move our data 1 over. So we'll do that. And then it turns out that like you don't actually need this merge anymore, so it's fine. And then I missed one thing, which is you need to state that you're merging x1 so that you can say these two branches are the same, but this merge would disappear and this merge would disappear because all of that would be useless because we know what 32 is. And then it turns out we don't even need to actually do that calculation in that shift at all because we know the number. So we'll just calculate the number. And so it's going to be 64. And we'll just save 64 and delete all of this code. And so that is what you'll typically see a compiler do. And if you're ever trying to optimize code and you like bring out your code into a separate piece of like into a separate file, you try to optimize it and you run your compiler and it takes 0 seconds, something like that might happen where you let your function inline or something like that. And your compiler decided, well, I know what the number is. Here's the number, we're done, right? So compilers will do a couple optimizations, I'll tell you them. They'll do function inlining. So because the function, the idea of a function is that you jump to some other instruction to run that instruction jump back, that's some time that is taken and also things about cache, and we'll talk about that. But we don't want to be able to do that. So if you're calling a function, you'll inline it here. Other things you'll want to do, strength reduction we talked about dead code elimination, constant propagation. You have things like if you're in a loop and you have something that you calculate every time in the loop, you can take that to the top of the loop outside of it and calculate it once. It's called loop invariance. Other things you can do, you can have something like loop induction variables, where if you ever have like a variable that says like I equals 0, I plus plus, and then some condition, that means what you're actually doing, if you don't modify I inside that loop, is you can say, well, I know that if I'm multiplying I by 2 every single loop, that means what I'm doing is I'm just adding 2 to I every single loop, right? Because your number will be 0, 2, and so on. So you'll just keep adding 2, and you'll save that variable at the top because multiplies are more expensive than additions. And you'll see that if you do like digital logic. Is there any other like major ones? I don't think there's any other major optimizations that compilers will do that you should be aware of. But those are like the big boys. Certain things like that redundant stuff, like if you have like an operation that like adds 2 and then subtracts 2, maybe you should remove that and store them in 2 different variables. But yeah, we'll do something like that. And then this is pretty simple to transform into assembly. If you know how assembly works, you'll actually just know that this is going to be basically what you want to output. And you're just going to turn this into like binary. And we'll just call it like x86, right? Let's say that's what you wanted to produce. That's what you would produce. Now, there's a couple different targets here. So the first target I said was x86, but you could actually just target any of these. That would be no problem. This format lets you target that, and most formats do. So you can target any instructions that you have here, and which is why you can have a compiler. For example, the GCC compiler can compile to x86, but can also compile to ARM. And so you'll have different targets like that. You can also have a target just called like eval. And this is an interpreter now, right? So you could even skip the SSA step and just start interpreting from the AST, but often we'll move into something like SSA or 3 address code which is kind of similar to SSA, but you don't need the requirement of single assignment. Just because if you have a loop, then you probably don't want to figure out where the top of the loop is in a tree. So you'll have it in a linear format. That's evaluation. You'll have interpreters, compilers, and then you have another thing called just-in-time compilers, where you output your own custom format, right? And then you'll go to evaluation, or you'll go to binary and execute it live. The reason why I say evaluation for a just-in-time compiler is, in my mind, evaluation is just the process of going through some format and producing a result, which kind of is all of these. So in my mind, all of this is evaluation. And then this is all just compilers. But we can call these different things. You can call this a just-in-time compiler. And you can call this a compiler. You can call this an interpreter. They're all kind of just different stages of the same thing. And so if you want to understand the performance of something like an interpreter, you have to understand what steps did you take here. Because I said each step here, you could do many different things, right? And so you have to understand what is your system actually going to do, and what is the code I'm writing actually going to do. And so this is the system that we have for producing our output. The last thing that we have is, if you produce a binary output, what are you going to do? You're going to load that into memory, and then you're just going to ask the computer to run it. That's it. That's all that happens. Now, you might have libraries, so you might load that as well, and then just tell your code where the library is. Nothing crazy. And that idea is called dynamic linking, where you load a library and then you run your code with the library. You could do this statically. Static ones will just take two sets of binary with all the labels here of each position, because sometimes you need to be able to say, oh, I have like a print. That's a label that I don't know about. You need to replace that with it. And so you'll go in and you'll replace those. And so that's the linking steps. You can do them at different times. It doesn't really matter. So that's like generally how the execution pipeline works, and like how you actually get from your text to the computer, like what the start of the computer. And from there, you could call it black magic if you want, but we're going to go into what actually the computer will do with this. I won't be writing binary on the blackboard because I don't memorize assembly binary. But yeah, do we have any questions about the pipeline system here at all? We're all good with that? Cool. Yeah. So we don't have any questions about like the compiler, linking phase, anything about optimization, nothing? We're all good? Very surprising. Like, I just like dumped a bunch of information on you and you're fine with it. I'll erase it then. Okay, so are we tired? Do you guys want like a small break, or should I keep going? What do you guys want? What system do we want here? Because like, I can keep going, but all right, bet. What? We do have a compilers course, but apparently it sucks. So unfortunate. I wanted to take it, but I heard it was bad. It's fine, I learned it myself. So the next part is actually going to be a little difficult to explain all in one go. And so there's going to be some gaps that you're going to have for sure. I do want you to stop me and ask questions the moment you feel like I'm missing something, because I'm a little lost in the sauce with the terminology. So I'm gonna just start saying things, and you're gonna be confused because you don't know what the word means. But I promise you, it's not complex. It's just the word is stupid. It was made by like 30 different companies, or one, Intel. So we're going to be talking about one company, which is Intel. We're going to be talking about one chip from that company, which is the Skylake chip microarchitecture. And we're going to be talking about x86, obviously, because Intel runs most of their chips on x86. Now, this can extend to other processors. If you just kind of squint at this processor that I'm going to be talking about, you'll be able to understand the majority of other processors. But it's going to be a lot of specific knowledge about Skylake that you could bring to other ones. You just don't want to bring the exact specific pieces that I'm bringing. Okay, this is just an example so that you can understand the situation that we have with the Skylake architecture. And the reason why I chose Skylake is because it relates to other microarchitectures that we've had. So Skylake is one of the architectures that we've been running for Intel for a long time, because Intel was trying to get to like a lower nanometer die, but they've been having a lot of problems with it during this time after the release of Skylake. So they just kind of rehashed Skylake a bunch of times, and it turns out Skylake was kind of a rehash of one called Haswell. So for like maybe anywhere from like 5 to 8 years, we've been running the exact same style of chip. They've just been making it slightly better throughout that time. And then eventually some things like their newer microarchitectures like Alder Lake came out, and then we actually had new microarchitectural changes that actually were like quite like groundbreaking, I guess. And then also AMD kind of like is doing their own thing, and Intel's crying about it. So we'll talk about Skylake. So the first thing that I want to talk about is just CPU in general. A lot of people have seen this idea. You have the idea that you can take your, let's say your instruction set architecture, right? Your instruction set, the x86 code, that binary will read it in from the CPU side. This is what the CPU will do. It will take that and it will go and fetch the instruction that it needs to run, right? And then it will take that instruction and it'll do something simple. It'll just figure out what that instruction needs to be done, right? So like, what does it mean? Just exactly the same thing that we did earlier. Now, some CPUs don't have to do this. The CPUs that are not variable length often will not do this. So some people complain about RISC versus CISC, because that's one of the cases where people go, variable length kind of sucks for the CPU. It could be true, but it also saves space sometimes, as you know, with UTF-8. So we're not really fully 100% sure on that one, but let's just pretend that they're right. It doesn't matter. You could skip this decode step. The other thing is that you'll execute it. So execution is kind of like when we outputted our binary. It's the last step that really has large meaning. And then after execution, we're going to do two more things. We're going to do a run into our memory, right? Because the CPU has its own registers and its own variables that it's going to be handling. We're going to go to the memory and we're going to go update anything that we need to update. The other thing we're going to do is we're going to update, right. So we're going to update or write back those updated executed instructions on our registers and update the registers that we need to update. Now, this sort of memory write-back system might be in a different order sometimes, and this is like not always the CPU. Sometimes you squash them all together. But modern CPUs will break them apart for one major reason. I'm going to steal an analogy. So imagine if you had a machine that can wash your clothes and also dry your clothes, right? And so you want to go and wash your clothes. You have like a couple loads to do. So you dump the clothes in and you let it run. Now you have to wait. Let's say the whole cycle is 2 hours. So now you have to wait 2 hours between each one. So let's say you have 4 baskets, right? You have 4 baskets and you want to handle each one. So you're going to do one big cycle for the wash and one big cycle for the heat, right? And then you're going to do the same thing again and again and again. And I'm not going to write them all, right? And you know what? We'll go with 2 because I don't want to draw them all. If we didn't do this, then we'd do something like we'd break this machine into 2 pieces. And we'd say we want a washing machine and a heater. And then we'll take one basket, we'll go wash it. And the moment it's done, we'll put it in the heater and we can start washing a new one. This is called pipelining. The benefit is that if you have the 2 baskets, you'll get a wash cycle, you'll get a heat cycle, but then you can start the next wash cycle immediately and you'll end earlier, right? It's the benefit of pipelining. The CPU is pipeline. That's why we have different stages here. Because if you let the instruction run all the way through, all the way to the end, all of this circuitry is just waiting. It's doing nothing, right? So we actually do some extra work to figure out how to break them apart and like lockstep them to doing specific pieces in steps so that we can actually feed more instruction through with higher throughput. And so this is what throughput means. So the latency to go wash one and heat one is 2 hours, right? But the throughput is different. The throughput here, we can say it takes, we can get 1 in every 2, right? But in this case, we can get 1 in every 1, right? So you can see we can output 1 every single hour. We can output 1 every 2 hours. That's higher throughput. And it's the same thing situation over here. Now, instead of hours, we talk about clock cycles. So all the electrical people know when you have a system that is running and you want to lockstep pieces together, you'll do something like a clock cycle. And this is a volt, imagine your voltmeter. This is what it's going to look like, right? And so on this rising clock, often it's on the rising clock. It was just like for fun. I don't know. We all decided that it was going to be on the rising clock that we lockstep everything at the same time, right? Now, a couple things. If you ever see the word double data rate, it means that we're actually using the down clock, right? So we're using the rising edge and the falling edge of that clock cycle to actually do things. So if you have a double data rate chip, your DRAM, your DDR chip is doing a rising and falling data step. So it's doing it on both clocks, both sides of the clock. Your CPU will do it on the rising edge for the most part. And so each time you rise on this clock, you will step from one to the next piece of this cycle. So an instruction will fetch and an instruction gets decoded and executed and so on. Now this is kind of not perfect in a model because this is kind of outdated. We don't do just one instruction at a time because as I've been saying earlier, some things like multiply or divide will take longer time, more cycles. That means if one of them stalls, let's say at execute, and you go to divide and it takes, I don't know, 80 cycles, everything stalls. The whole system stalls. And you don't want to stall because, you know, we're just waiting for that guy to finish again. So we have the same situation as before. So this one we pipeline, right? Pipeline. We break apart our circuits. The next thing that we're going to do is we're going to say, okay, well, we have now a problem. We want to be able to execute more, like while it's stalling, right? While it's stalling, I want to do more things. So what we do is we say, okay, so now I'm going to put more washing machines and more dryers, right? So we'll put another washing machine here. And now you can start doing more cycles on each set of those like washing machine and dryers, right? And so, oh, I missed the box. And so this idea here is what we call Superscalar. Okay, Superscalar is when you basically just copy paste the same thing and or like have more things that you can do at the same time. And so A lot of these things will do multiple things. Fetch will fetch multiple instructions at the same time. Decode will do multiple, so on, right? We'll do a lot of things at the same time. And so let's just annotate that. This is out of order, oh my God, execution, right? Oh, I used the wrong word, guys. This is Superscalar. And so we'll do multiple things at the same time, is Superscalar. Now, the other thing that we want to do is out of order execution. So let's say you have an instruction where you have a multiply, or you have like a divide, right? You divide one register by another one and save it into that register, right? So you divide 1 by 2 and you save it into 1. Then what you do is you say, I need to multiply this register 1 by itself. Okay, I want to square it. Okay. Then the next thing I want to do is I want to add register 3 by register 2. Okay. So if we do this in order, we take this divide, we put it into the pipeline. We take this multiply, we put it into the pipeline. And then it turns out, well, actually the multiply can't run yet. So we're stuck here at the decode phase where we're like, okay, well, I can't run that divide. Not possible. One thing we can do is we can do this add. This add does not depend on R1. R1 is calculated here, but R3 and R2 are already here, right? So we can run that as well. So we can go out of order. This instruction will run after this one. But we have to make sure a couple of things. We have to make sure that they actually commit to memory in the right order. And we actually have to have the right registers at the end of the system. So we'll make sure that this winds up being in order eventually. But in the moment when we go to execute it, we actually make it go out of order. And we try to figure out, OK, what is being used by my CPU right now? What can I use? And what can I put this into? We can have different execution ports here. So we'll have things like the math operators. We'll have things like, well, different types of math operators, right? We'll have floating points, decimal. You'll have integer style, or you'll have like some special operators, right? And those ones will have their own execution units, right? Their own circuitry. And we'll put them on different sets. The different sets are these, and we'll call them ports, okay? Now, different ports will have a lot of different execution units. Just because having many ports is very expensive to put onto a CPU because it's very hard to route everything. So we'll just have a couple different ports that address a lot of different execution units. These execution units might get tied up by some operation, as we said. And so not only are you looking for dependencies, you're also looking for ports that you're not using to fill up. Right? So if I'm doing a divide and divides on port 0, and I'm doing a multiply and multiplies on port 1, I can just throw multiply on port 1 if a divide's already running or something like that. So we'll try to fill things out as best we can, and that's going to be out of order execution. Now we can do that. Right. And so these are the principles. You have out of order execution, pipelining, and superscalar CPUs. Big word. And the majority of our CPU is bound by these ideas, and it's very difficult to make these ideas work out. And you'll see very soon, as I draw it out, it's going to be a nightmare. There are a lot of steps in making this work, and you'll find out that this idea of a CPU is no longer valid because this is too simple. It's too linear. It's not everything a CPU will do. So let's start with memory. Okay. So you have let's section this off. You have your RAM module here, and let's say you loaded your program into RAM. Okay, it's already in there somewhere. And you already have the right permissions and everything. Your operating system has set up everything. We're just going to pretend everything is worked out. The next thing we're going to do is we're going to send that over to the CPU, I guess. Yeah, we'll go to the motherboard first. Oh my God. We'll go to the motherboard first, and we will just pass our data over, and the CPU probably requested it at some point. Then what we're going to do is we're going to send it over to the CPU, and the CPU, I'm going to draw way bigger than the motherboard because that's definitely how that works. And we're going to have this thing called a system agent, which has a lot of things inside of it. It's known for I/O. I believe it handles things like PCIe, internet, I believe. I don't really remember. Those parts are not really important to me. The main part that was important is we have a memory controller. Right? We have our memory controller, and that thing will do all the memory stuff. Then we will pass that to the rest of our CPU, and we'll have these things called level 3 cache. Right? Level 3 cache is the third lowest level of the cache. The bigger the number, typically the bigger the cache is, and typically the farther away it is from the actual execution of the instructions. We use this because this is a long trip to make, and we don't want to wait that amount of time every single time we want to go and do something to the memory. So we make our own little cache. We make a copy of our RAM, but just a part of it. This L3 is a lot smaller. Just scale this down. And then let's say we have just a single connect between a dual core CPU, right? And there might be an integrated graphics underneath, but like no one cares about that. The L3 will have different connection styles. You often see there's a big problem inside of parallel programming when you have multiple cores is how do we connect all of these guys together, okay? If you have a dual core system, it's not that deep. You just connect them, right? Just a couple wires in there, you're set. Once you start hitting crazy amounts, you're starting to go, well, this is a pain to connect everyone together. Like, as you know, if you have a fully connected graph, you're gonna, as the number grows, you're gonna get like very humongous numbers. I think it's factorial or something. I don't know. I'm not a computer science student. So what we'll have to do is we'll have different ways to connect. The classical way of connecting is a mesh network where you just connect literally everything, I think. Wait, no. The mesh network is a grid. The mesh network is a grid kind of like downtown, a nightmare. It's just traffic all the time. And there's too many roads, and that's a lot of money. So sometimes you'll do what Intel did, and you'll make a ring buffer where you connect all the cores with a ring and connect the memory with that ring. And so each stop in that ring is kind of like a train. It's a circle train, and that ring, each stop will have a stepping amount, and that's going to also step by a different clock, I believe, than the CPU clock. I'm not entirely sure, but I believe it was a slower clock. Ring buffer. So ring buffer is just a, oh, sorry, I used ring buffer. What am I? Ring interconnect, I believe. What were you missing? Okay. Yes, so we have to connect our L3 and all our cores together. And so the way we do that, we have multiple ways. We have things like mesh, where you have grid, right? Or you have like a full connected graph, or you have a ring, right? A ring just connects each one to the next one circularly, right? That's all. Yeah. So I want to expand this CPU out, and we're going to talk about the CPU. So we get our instructions and first our instructions. We'll get our instructions all the way through to L3. You might pull some data in too, and you'll put them into your cores using whatever interconnect style you want to have. And then inside the CPU is a nightmare. Also, all of these are individually nightmares. I think this is probably one of the smallest parts. The CPU is probably one of the smaller parts of this entire thing. There's a lot of like even just writing the word memory here should have been like, I don't know, like 3 semesters worth of me talking. But We're just going to talk about the small part, which is the part that the software people will actually care about. The programming, you want to care about this the most. RAM is probably the second most important for you, but this is very important. So this will be, we'll start here at L2. Okay, L2 cache is just the next cache that is going to get pulled in by L3, and then we're also going to have something which is completely unrelated, and I hate how they name it. It's the L2 TLB I, right? The instruction translation look ahead buffer. Worst name ever, IBM. This L2 TLBI is the second level of the TLB, which is a cache for translations of virtual addresses. So as many of you know, you have a process, and that process will not look at all of memory at the same time unless you're the kernel. That process will look at memory as if it owned the entire memory space, and then sometimes it'll access some data that it shouldn't have, and you'll seg fault, and you'll get a general protection fault. It's great. But we don't want our process to be able to look at other programs' memory, because that means you could create a program to read someone's password out of memory. So we create our own process space, and we'll do translations between your fake address and physical address. So these are our cached lookups for those translations. Okay. This is actually physically below it on the chip, but I put it above because the diagram is going to get real messy. Okay. I'm going to try to keep the positions of everything relatively similar for the electrical people, but it's going to be a little fake. The next thing is we're going to pull this L2 into L1. And just for your note, I'll just put an L1 TLB here as well. And so we're going to pull that data into L2. Just a note, the Skylake L2 TLB is 256 kilobytes. So if it doesn't fit into 260 kilobytes, you're going to be going out to L3. So I suggest, if you can, if you're optimizing for Skylake, fit it inside of this guy at least. And then this one's 32 kilobytes. So if you're thrashing between those two, try not to, I guess. And here's where the nightmare begins. We're going to get our instruction fetched, just like we had over there. Instruction fetch, right? We're going to fetch our instruction. We're going to pull 16, at most 16 bytes into this instruction, during this instruction fetch, okay? And this instruction fetch, its job is to do the variable length instructions stuff. So the instructions, as you know, in x86 are variable length, and we need to be able to find where all those instructions are and begin decoding them. So that's that guy's job. We'll pull out 16 bytes-ish. The next part is we will push that into our instruction queue. Oh, I'm running out of space, eh? This instruction queue holds 50 instructions-ish, and then we will we'll do an optimization here. So a couple of our instructions are always next to each other and also can be executed with each other. So instead of taking up multiple entries, as I said, this thing takes up 50 entries, right? So you can hold 50 entries in here. That's going to be the same for a lot of these components that I'm going to be drawing. There's going to be a number of entries you can put into buffers. So preferably, instructions that are always going to be next to each other should maybe become one instruction. And so that's what we call macro fusion. So you have this thing called macro fusion. I'm not going to write the whole word. So Macrofusion is just the idea that you will take those instructions and merge them together. In the Skylake CPU, this literally only just means branch fusion. You will merge two branches, or a branch and a test together. So a compare and a jump, or a conditional jump. Those two generally get merged together in the Skylake CPU. But in theory, you could merge more. We just don't need to. So that's what's happening in the instruction queue. We're also just queuing them up for other things if the rest of the data gets like stalled for some reason. The next step of this is we will go and decode. So we're going to decode our data. We have a couple things in here. You have the complex, and then you have three simple decoders, which I made not enough space to write the word simple. That's how simple they are. We'll just trust that it says simple. So the way that this works is that some x86 instructions on the Skylake CPU will produce many things that we call micro operations. As you know, we have variable length instructions. It's a pain to use variable length instructions throughout the rest of the CPU. So what we do is we create non-variable length instructions in the CPU. We just don't want to deal with that. Some things are a pain. When we create, let's roll it back. So to do that, we actually convert them into this other format called micro operations, and they are proprietary. You don't actually know what they are, but you know that they exist. And we have to be able to convert our instructions into specific operations, but sometimes you can't. And so that's what the complex decoder generally is for. Some things like add with carry or vectorized moves will do multiple micro operations at once. So you'll use this complex decoder to output multiple operations. You'll have up to 4. I don't know why I'm annotating only these ones, so I'm going to stop annotating. Maybe I'll just put the annotations just for the decoders. And then you'll have up to 5. So these are the numbers of micro operations that are going to come out of these, and we can have up to 5. So this complex decoder will actually start turning off the simple decoders, or at least masking them out, whenever it starts running more micro operations. So if you push anything into the complex decoder that winds up taking like 3, 4 micro operations, these simple decoders are starting to turn off, and you will get a lower throughput. So you'll get to up to 4 micro ops, but you'll get less instructions through. That's why we have this queue. But you don't want that to happen. And so preferably you would choose instructions, if possible, that wouldn't produce or that wouldn't hit this complex decoder too often, especially in the hot loop if you are somehow repeatedly hitting this pass. And I'll talk about why you probably, hopefully, will never hit that pass in a hot loop. Hopefully. I'm going to make some space for myself here. So this is the main path that we take. The other thing that we have, I'm getting really weird here. This is really bad. We're going to have this thing called microcode. I don't know if you guys have ever heard of microcode. So the Microcode Sequencer is something that will produce microcode, or a bunch of micro operations, for one instruction. And so let me just try to draw an arrow here to here. This microcode sequencer is actually over here in the CPU diagram, but I'm going to put it over here because I'm running out of space. The sequencer, its job is to take a really complex instruction or something really special, and it will output repeatedly. This is really bad. I shouldn't be an electrical engineer, is what I learned. I can't draw straight lines. But you can output up to 4 micro operations per cycle. I'm going to use C for cycle. I'm not going to write the whole thing. The will get flown through here. For example, Intel has multiple microcode updates, and that is probably where it's updating the CPU. The microcode will change how the CPU works on instructions. It will change potentially what things run during the life cycle of the CPU and what things get activated, and maybe flushing store buffers, flushing line fill buffers, and we'll talk about all of those buffers later. But this thing can do a lot of interesting things and really complex things. And sometimes I feel like maybe we shouldn't have something like that. But, you know, I don't know. I'm not a CPU engineer. And so we will select out of all of those using a mux. Mux lets you select. That's what it does. And so we'll have one other path, and it's that we don't want to do this every single time we do something in a loop, right? So if I go to do something in a loop and I just fetch it every single time and parse it out, that's like the dumbest version of the interpreter that I talked about, where we go back to the AST or even back to the file and we just do it all over again. That's dumb. So instead of doing that, how about we don't, and we push it into this thing that we call a micro-op cache. This cache holds 1.5 thousand or 1,500 entries-ish. It depends on how many lines you're working with, and there's different things about associativity and whatever. If you did database or caching, you'll know what I mean by that. But this thing will output up to six micro operations, depending on how your instructions are spread out and how many branches you have, because branches will actually cut off certain lines in these micro op caches. But if you wanted to know more about that, then you're already too deep. So from there, we'll take this mess and we'll just pipe it down into the next stage of the CPU. And we're starting to enter the nightmare, I guess. Maybe this was already a nightmare, but worse, I guess. We just push it into a queue first. Maybe I'll push that way after this. Decode. So we have an instruction decode queue. Oh my God, I hate this so much. The instruction decode queue will do two things. You have one thing called LSD. Yeah, the LSD. It doesn't exist on Skylake anymore. We turned it off using a microcode sequencer because there was a bug in it with the partial registers. But the LSD is a loop stream detector. It detects loops, and it kind of acts like a micro-op cache. It detects loops, and I believe it does like 40 instructions max or something like that. And it takes a couple times to go through this system to be able to detect it, and it would dump out the code instead of all of this doing it, and it would actually just turn it off. Same thing with the micro-op cache, it would just turn it off. That way we save power, because CPUs draw a lot of power and we want to save power, so we just turn things off when we feel like it. That thing's no longer on Skylake though, unfortunately. Yeah, so we'll talk about that, but yeah, so there will be a stage where you, well, first of all, the rest of the CPU will actually notify this part here. It's not like you turn off the entire thing. It'll like turn on pieces whenever it feels like it, or it'll go talk to the cache and say, hey, we still are going, or it'll talk to other parts of the circuitry, right? So it's not like it's actually completely off, because you can just turn it on again with some power, but we turn off some of it. Definitely not the caches here. They don't generally go off. And then the other thing that we have here is called microfusion. And we love, oh, I just decided to write micro-op. Microfusion. So microfusion, just like macrofusion, merges things. But in the case of microfusion, the operations don't actually execute together. So in the case of macrofusion, you took two instructions, you literally made them one micro operation. But in microfusion, microfusion takes two micro operations, merges them together until execution. When it merges, it removes them again. I actually lied because microfusion actually happens here. But I remember that the diagram I saw actually put it here. I don't know why it put it there. Because it's impossible to put it there. I'll tell you why. In 1 second when I find out where to put it. We'll put it here. Micro. So microfusion happens in the decode, or during, or somewhere in the decoder, and this makes no sense to put it here, because what's going to happen is we want to save some space in the micro-op cache sometimes. And so we'll do microfusion to save space in the micro-op cache. We'll save space in the number of entries throughout this CPU. But sometimes in some older architectures or some instructions, you can't actually have them together because you're going to actually need to split them eventually. And if you do microfusion here, then you don't actually wind up putting it in the micro-op cache. So you have to do it here. But I saw a diagram put it here. So we'll put it there. The other thing about micro-op cache is that you need to split it in the instruction decode queue or the renaming phase, because the renaming phase and the instruction decode queue needs to be able to sometimes schedule two micro operations that have been microfused together separately. And so we can't possibly do it here. I'm still angry about that. The other thing we'll have, and this is where we really depart from the actual CPU die shot, because I can't do things vertically anymore. The next few things that I'm going to draw here should all be vertical right here. I just don't have the space. We will say we need a rename. So we'll take our rename, which is something that I'll talk about. Rename / dispatch. So this unit here, called the rename dispatch unit, will pull instructions out of the decode queue, which this queue has like 128 entries. And it will push them into, it does all of the coordination, right? It's like kind of like the CPU of the CPU in the way that it manages out of order execution. And so this is the part that really gets messy, because what's going to happen here is we're going to go and we're going to push something, we're going to push instructions or snapshots into what we call a branch order buffer. And this branch order buffer will be used later, as you will see, to roll back CPU state if we ever make a mistake. For example, if there's an exception, right? So if you throw a floating point exception, you can roll back state or something like that. The other thing that we're going to go contact is the register allocation table. Register So the register allocation table lets us actually map registers from, we have these fake registers, okay, in our CPU. Because we're doing things like out of order execution, we probably don't want to be able to just like throw things directly into like permanent memory immediately. And so we have these things called architectural registers. Architectural registers are just the ones floating around in space throughout the rest of the CPU, doing whatever they want. And they will be tracked here in the register allocation table, and they will be mapped onto physical registers where they will actually be stored when they complete. And this guy or the rename guy will actually do certain different algorithms like scoreboarding or Tomasulo algorithm to keep track of which instructions are complete, which ones have dependencies still running, which ones are in flight, and whatnot. And it will make sure that instructions get committed to memory or physical registers when the instructions actually, like in the original order of the program. So that's the job of the rename people. Let's put a down arrow there. And then the other thing that we have is called a reorder buffer. The reorder buffer is actually where we store our instructions that we want to run. So we have reorder that's typically written as Rob, which I don't know how that happens. But the reorder buffer has 224 entries in the Skylake, and it will basically also help with the rename dispatch system to keep track of everything, right? It's part of that Tomasulo algorithm. And we will also now, should I write that now? No, it's fine. The reorder buffer will push it into the out of order execution resources. I'm not going to write the full word because it seems unnecessary. The out of order resources, execution resources exists like this. We have different sets. We have the integer register file. So we have a register file for all of our standard sizes, like, you know, 4 bytes, 4-byte registers that we can store all the data inside of, you know. So sometimes 4 if you want, but 4 bytes seems about reasonable. And that's like where we store integers. Crazy thought. You will also have the vector register file. So the vector register file is for wide operations. This is one of our key points of our CPU that a lot of people, for some reason, just never know about. And it's not even a deep point. It's literally, you can just store registers as a group of registers in one big long register. It's what we call a vectorized register. And and you can have multiple registers get operated on at the same time. So you can run like a vectorized add, and that will add all the registers at the same, like it's not a crazy thought. You can do less work in the rest of this humongous thing to send one instruction to do 4 things at one time, and that's where they get stored. The other thing you have is the MXCSR. The MXCSR is the register file. It's a flag file used for the instruction set that we call SSE, SIMD streaming extension. That it's just used to tell you, like, let's say if you don't want your vectorized operations to crash on like floating point exceptions, then you'll set flags inside of the MXCSR, and that will mask out that. The other thing is you have this out-of-date, very legacy register file, x87 MMX, right? x87 and MMX are very, very rarely used, and you'll never see them ever. I hope you don't see them, because these two are for basically the x87 register is it's an 80-bit floating point register, and this register is slow, and it's a pain to use. And if you want to convert between them, it's kind of sucks. So we don't use it. The MMX is basically our way of shoving integers into there. It's an extension, and it also sucks because you can't use it with the floating point. So then no one winded up using them, so we don't use them, I guess. And I can tell you their sizes. This one is 168 entries, I believe. And then this one should be like, no, this is 180, this is 168, this is 8, and this is 128. And so you can see that the vectorized ones and the integer ones are the largest amount. And so, you know, don't be afraid to use them. try your best. And so don't worry about the CPU not having enough space, but as you know, the x86 architecture will actually have less registers than this because we're doing things like out of order execution. And we're doing all sorts of like nonsense here. And we have things called renaming, where if you have, for example, an operation that like puts something into RAX and then modifies it, and then puts another thing to RAX and then modifies it, these two registers are not actually the same register. If you think about it, they're completely unrelated. Like if I put 5 into A, and then if I put if I say A++, and then if you have A and you put 6 in here and you have A++, why would I use the same register for both of these? I wouldn't use the same register for both of them. And so the rename will say, why would I do that? And so every single time you assign at all of these will be different registers. Every single line here will be a different register. We will use a different one for each one because we can go, okay, single static assignment again, and we just apply it to all values going on into the future. We just use that, okay? And so we rename whenever we want to do something so that we can start doing more operations in the future, earlier, faster. And so that's why we have so many registers in here. We just, every single operation just winds up using a new register. And so that's where that goes. The other things, we have the final pieces of this huge piece. And this isn't even, I'm gonna be honest with you, this is not even close to like what actually happens. Yeah, it's not even close. Each piece in here expands immensely. I could take like just one simple decoder and expand it and do a whole research study on that one simple decoder right there, right? So this is not the end, but I won't go into it because I don't even know it. We have things like the math scheduler and the address generation unit scheduler, which for some reason I decided were different sizes, but they're not. Well, this one's bigger. This one is 58 and this one's 39. We will, I don't want to draw each port like number. Do I? I could. So the math scheduler will have a couple different pieces here. We have port 0, port 1, port 5, port 6, and port 4. The AGU will take all the other ports. So, okay, that goes. And so we'll take these ports here, 2, 3, and 7. These ones here are part of memory, okay? So these things will talk to the memory. These ports here will have address generation units, so they'll go and calculate addresses. You'll give them registers or something, and they'll go figure out what the address is. And then maybe you can also store things using them or load things. This is primarily usage of it. Number 4 will do storing as well. It's just part of the math scheduler because you can do, we'll talk about that in a second. And these guys will go out. And I'm just going to not actually remember how they work. And I'm just going to put them into the store buffer. The store buffer and the load buffer. I cased them differently. Let's do that. Sure, that looks cursed. That's not how that works, but it's okay. And then we'll say the L1, damn it. And this is where I hate all of this, because this is actually the L1I. And this is completely unrelated to the other L1. And it's also completely unrelated to this other L1, because that L1I is the instruction cache. This is the data cache. And we just use L1 at the front, because we decided that the first thing would be the most useless part of it, and you actually cared about the fact that it was data and instructions. And these ones are unified, which means they merge both of them. And so you will pull data into there. And the way you pull data is you have this queue. merging. Yes, no problem. So this stores instructions, right? So the lines for the instructions. And this one stores the data lines. This one will store both. There's no real distinction between them. It's just that they're in different parts of the CPU. So we have two different caches for this. Yeah. Exactly, right? And that's why I hate why we call this L1 data cache, because they're not related at all. That's really cool. But yeah, when we pull this data in, we'll use these things called line fill buffers. Oh my God, I wrote this like so small. So the line fill buffers, there's like 10 entries in there for like running entries, because if L1 misses, if your data is not in there, then you have to go wait for it to go to L2. So we have these buffers to pull from L2. And then we have, why did I draw it like that? Store buffer will store. That's how it works. The load buffer loads. And the two loads. That might be wrong, but I hope it's right. I think loads are more common. So we'll have storing and we'll have loading. One issue with this is that, let's say you do a store and then you do a load immediately after to the exact same address, you have an issue. If you store first and then you load, so if the store happens to run through first and the load happens after because out of order execution, then, oh, that's cool. That's cool. Then what's going to happen is that you're going to get the right data, right? Because the store happens to go through first and then the load happens. It's perfect. But if the load happens to go in first, you're going to get old data, right? So we need this thing called a store forward. So we're going to forward our data. And I'm not even going to write the word properly, apparently. Store forwarding takes a lot of time depending on where your addresses are. If they're completely aligned, it's like a couple cycles. If they're unaligned, or if one of the loads are inside of the bigger store, you're going to have issues with forwarding, and they're going to take like multiple cycles, like 15 cycles or so, maybe more. And so it takes a lot of time to do forwarding. Other things about this to know is sometimes the store buffer is split into two. AMD did that on Zen 4 when they said, okay, so well, we can do a buffer for storing where the store is going out to L1. And we can do a buffer for when it's coming back. So before we retire the instruction, before we say, okay, we're done, we'll also track those separately. And we can have a much larger amount of those ones running. And so that's an optimization that AMD did. But that doesn't matter too much. What we have is when these loads and stores go in, we'll push them into buffers. And then those buffers will make sure that they handle any dependencies between them. And they'll push into LD or level one data cache. And then we'll pull from L2 if we need to. Hopefully we don't. And so that's how the memory subsystem kind of works. In a broad overview. Nothing really happened there, but we will get the output of these math operations as well. These math operations, as I've been saying, multiply, add, vectorize, add, like bit scans, everything. Everything comes in and gets applied into these ports out of order and scalarly, and then we will pull them out. We will push them back into the math scheduler, and we will also push them out to the reorder buffer. And then the reorder buffer will push them out or interact with the register allocation table. And so there's a mess here, and let me talk to you about it. So the first thing is, if you have two instructions, and the first instruction produces R1, and the second instruction consumes R1, that means that you have to be able to say, okay, well, I want to get that result from that, like let's say it goes through port 0. I need to get it back to myself. So I give it to the math scheduler so it can do it. And the math scheduler will say, okay, let's tell the reorder buffer that that instruction's done so we can, free the resources that we use to track this thing. And then the reorder buffer will tell the register allocation table, okay, we're done with that register. We obviously push it into the math scheduler first instead of pushing it to the reorder buffer because we don't want to wait for that instruction to go all the way through the reorder buffer, get retired, get applied into the out of order resources, and then pushed through the registers up into the scheduler, and then the whole thing happens. So we just push into ourselves. And then, yeah, so this is the basic outline, and you'll have an instruction push through a bunch of instructions. Oh, welcome. And so we'll have a bunch of instructions get pushed through into the fetch section, and we will we'll queue them up. We'll do an optimization called macrofusion. We'll decode them. We'll merge them together into this system where we have the microcode sequencer, the microop cache where we want to not decode every single time we run through our code. And we'll have a microcode sequencer handle any super complex instructions, and then we'll push them into our decode queue. We'll not do loop stream detection. We'll make sure that our micro operations are fused together so that we can split them apart at math operations or address generation. And then we'll also split them apart at instruction decode queue or the rename if we need to schedule them completely differently. And then once we go through here, this is the out of order execution area. So this entire section here is known as the back end of the CPU. This is known as the front end of the CPU. This is where out of order starts appearing, and you will start using that algorithm, the scoreboard or the Tomasulo algorithm. Scoreboarding is the older one, Tomasulo is the newer one, and Tomasulo is a little better in terms of memory usage and the amount of stuff you have to track. And so we'll use that to rename our registers, like I talked about earlier, where we'll just create new registers every time we modify data, and then we will add them to the register allocation table. We'll update the reorder buffer with the entries, and then this operation will go through. We'll execute operations. We will do loads and stores. We'll push them into our cache or pull them out of our cache, make sure that the dependencies are managed, and then we'll also retire our instructions. So once the instructions are complete, we'll tell the reorder buffer and the rest of our out of order system, hey, we're done with this instruction, and now we're out. Now, that's a lot of work to do. And so I want to talk about what if you had an if statement or a branch or a function call. So if you have one of those, you will enter the fetch, and then you'll realize I can't fetch anything because I don't know where to fetch it from. If I branch, that means I'm going somewhere. Where? I have no idea. And so what we have is this thing to control the L1 cache fetching mechanism called the branch predictor. There are many different ways the branch predictor works, and it connects to a lot of the different systems in here, and you could make different techniques for it. The very old technique was saturating counters. Saturating counters is literally you just have a bit or a couple bits to represent whether or not you're going to take it, and you subtract from that number whenever you get it wrong, if you don't take it. And if you get it wrong and you do take it, or actually it doesn't matter, sorry. Whether or not you get it wrong, you'll increase it or decrease it whether or not you take or don't take. And so that's the saturating counter, but we found out very quickly that the saturating counter wasn't enough for complex patterns, because you could get a pattern where you'd be like, okay, so I'm going to take it. And then the pattern says don't take it, so you subtract. And then the next time you'd have to take it, so you mispredict every single time. So we made our branch predictor a little better, and we created a table. I have no idea where to use this. Y'all don't need this. You will take one of those saturating counters, right? You'll take one of those saturating counters where you can go forward and backwards on each set, whether you take or don't take. And you'll go to your self like this, and then you'll label them take and not taken for each of those. And you'll copy that down, and you will index them using the branch history. So I'm not going to draw all of them, but let's say 0, 0. So you haven't taken the branch twice in a row. That means you use this predictor, right? That's a branch history style prediction where you use saturating counters. There are many different more ways. You have the perceptron. If you've done statistics, then you'll use sort of statistical method to aggregate data in and do an analysis of which parts of this weight is wrong and update those weights and make sure that they kind of accurately represent this, this branch prediction or the branches that your code are doing. Now, this table can be used in conjunction with the predictor or the perceptron and other methods. This predictor, this branch table prediction method can be used for local branches specifically. So you could have multiple for local branches. You could have a global branch prediction method that, and a lot of systems will use global branch prediction where you go, okay, so I know that these two for loops are different and I know their addresses are different, but I'll just treat them all the same no matter what. There's obviously also tagged versions, which we call tag geometric history. It's where you have multiple different history lengths for your system. So like here, we're representing 2 bits of history, right? But that might not be enough for some patterns. So we'll have different tables with different lengths of histories that you can address into all at the same time. And the largest one that you hit, you'll use that prediction. And then the other thing is that you could have something like a agree predictor, which says, hey, that prediction is not generally accepted, so don't use that one, and just use this global prediction method instead. Or if you don't get any hits in your address table for that history set, then you will use some other prediction method like the global prediction, and then you'll update the system. And the system really acts kind of similarly to the perceptron, where you'll also update weights. You'll have weights for each of those. But if you wanted to go into branch prediction, that's a really cool area. You can use this in a lot of places. I remember one place where I could have used it, but I didn't realize I could. And it was when you were doing predictions on rock, paper, scissors. You had 2 robots or 2 programs compete against each other trying to do rock, paper, scissors. And you would guess what you should play out. And you could probably use a branch predictor for something like that. Yeah. Yes, very, very, very common. Compilers, not necessarily. It's a little harder for that because you can't actually tell what the programmer or what the data is going to be running. But something is very common that will happen that some people don't know about is called profile guided optimization, where you run your program, you generate a profile of it, and then you feed that profile into the compiler. And the compiler will create a new program that's based on that profile that you created that goes, oh, this branch is like always predicted. Okay, I'll put this above the other branch or something. And typically, branches are defaulted to not take. So you default to not take a branch. So often you'll find compilers will flip things and you'll be like, okay, the most common, or like whatever you wrote, it's going to run through the don't take first. Yeah, so that is something that does happen. But that's normally in high performance situations, and I wish we did it more, but we don't. I love profile guided optimization, really cool thing. Yeah, but generally, if you're a programmer and you want to write better code, then you probably do want to put that most likely, like most predictable branches at the top, because that branch, you'll basically never get it wrong. And what does happen when you get it wrong is this branch predictor informs your micro-op cache or your L1 cache to tell you, hey, you need to run the fetch, or you need to go push that data out because you hit this address or something like that, and you need to push that data into the rest of the CPU. So if you get it wrong, what happens is this branch order buffer that I was talking about earlier will keep that snapshot so that we can roll back this state, the microarchitectural register state, and remove any instructions or flush any instructions that we don't need, and remove any register that are storing things that we don't actually want, that are like incorrect data, right? And so that's what we call a branch misprediction. Branch misprediction is a very, very common way to lose performance in your code. And so you should, if possible, make your branches either more predictable by figuring out a better way to write your code, or use things like predicated moves or conditional moves. So you'll see things like cmov, where you calculate both sides of the branches, and then you'll conditionally move one branch into one of those registers so that you can have either of those branches, but you'll calculate both sides at the same time, no matter what. And so it's kind of like it linearizes both, because you run it all no matter what, and then you'll merge it. And sometimes your conditional move will be slower because obviously you're taking up more instructions, you're doing more work. But if you can remove dependencies and remove the amount of times you mispredict, hey, that's a win. Yeah, and I can talk about more things that we can have in here. Like, for example, I said the instruction fetch is 16 bytes. If you get that alignment wrong for the window for your code execution, then you could get your instructions getting out of, you could get your instructions into a position where you take more time to load them, especially if you have a length changing prefix. So if you have, if your binary starts with like 6.7 or 6.6 in your assembly, then you'll have, sorry, that's in hexadecimal. And if it starts with those, you have potentially something called a length changing prefix, where like one case of that is where you use a partial register. You use a 16-bit of a 32-bit. And so that might slow down the instruction fetch. So if you're bound, if you're speed bound by your instruction fetch or your front end, you definitely don't want to be using length changing prefixes, because you're going to stall your pipeline, especially if that length changing prefix is in the 14th byte, because that means that the length changing prefix will be at the end of that window, which means it can't tell how long it's going to be, but it can tell that it needs to stall. No, that's just when, you know how your code is just all linear? It reads it in 16 byte. So if you don't align it, yeah, exactly, right? So it just happens to be in that section. So if it happens to be in that section, you'll get a double stall, where you stall once because you go, oh, I don't know how long it is, I need to figure out how long it is. And then you'll get another stall on the next cycle where you go, okay, now I know how long it is, I need to find out how long the operation is. And then you do the whole thing, which is a nightmare. So you don't want that, and if you can, you avoid length changing prefixes if possible. That's for the compiler people, which none of you guys, I guess, are. Are you a compiler person? I don't know. But if you were a compiler person, you would definitely make sure that you tried to avoid a situation where you had a lot of those length changing prefixes, or if they're unaligned, you want to avoid that. In a hot loop, you definitely do. Other things are complex decoder. If you or macro fusion is a big one. If you split apart your test and your branch operation, then what will happen is that macro fusion won't happen, because you'll have an instruction in the way, right? So you want to have these two together so that you can have one micro operation output. I know some people will try to separate the test and the branch so that they can calculate it early, and then that flag will be ready in the flag register, and then the jump can happen earlier. But you could also have them together and reduce the amount of entries that are running through. And so that's a situation where you have to pick. You have to pick what situation are you running through. Are you running through a backend stall, or are you running through a front end stall? Or I guess one of the rename stall, I guess. The compiler will. Yes, often you'll find the compiler, if you try to write code in a way where you like figure out what the value is first and then you do the branch, it'll just put it together. Very common thing. So it'll make sure that you can do macro fusion. The other thing is microfusion. If you have things like memory operands, or if you have an operation where you're trying to like add to memory or something like that, you'll have multiple things. You'll have address store, you'll have data store, and then you'll have the actual operation, right? And so these things all go together, obviously, from your mind. So they figured, hey, we'll just output one micro operation that's fused together for those, and then we'll pass them through and we'll split them at the end and we'll run them all separately, right? Other things that you might want to note, try not to use that complex decoder. If possible, it stalls the other simple decoders. Try not to use anything that hits the microcode sequencer. That thing takes four micro operations per cycle, which means you can stall multiple cycles trying to output something that you that's a more complex instruction. For example, on ARM, I remember that the microcode sequencer started dumping a ton of micro operations because it didn't know how to do a divide, because divide didn't exist. So it just started dumping micro operations. And then other thing is micro-op cache. This is 1,500 entries-ish. So you want to make sure that your code fits in here if you're doing a loop, right? So if your loop is humongous and it's somehow passing that 1,500 range, maybe split it into 2 loops. I don't know. You try to figure out how to make it smaller so that you can not thrash this cache. You also want to make sure that these caches are all like within their like good range so that you're not thrashing between those. This is 32 kilobytes, and this is 256, and this is also 32. And then, as you can see, the micro-op cache can feed a lot faster than these other parts of the system. This is up to 5. This is all 6. So you can be dumping all of those. But note that the micro-op cache will cut its lines short if you have branches in them. So if you have multiple branches, they will take up multiple lines and stuff like that. And so you want to make sure that you don't have multiple branches in the same cache line. So just don't spam your branches, I guess. Yes, Intel has performance counters stored somewhere in the CPU, I don't know where. And you can query those performance counters using different methods. Different operating systems will have different things. But I remember VTune, I believe, Intel VTune should have something on that. And if you're on AMD, I don't know, I'm not an AMD guy, which I should be. What'd you say? Magic Trace? I don't, I haven't used that, no. I've only used VTune. But yeah, you can inspect your performance counters. I believe Linux has like perf also does performance counters. Yeah, so you can use that. Make sure you don't screw that up. You can also look at the assembly output if you wanted to actually figure out how many micro-ops are, like what's going to happen. You can use a site called Godbolt. Godbolt lets you decompile your code down into assembly. You can copy that assembly into something. Here, I'll write it for you. We'll write it here. .org. Yeah. Yeah, we have godbolt.org, and then we have, you're going to pass that information over to uops info code analyzer uops info. This thing will let you go and run simulations of your code. So uops info code analyzer has their own specified code analyzer that's statistically created for like based off of CPUs, or you could have other ones in there, like the Intel code analyzer exists in there. That one's pretty good for Intel, and I use that one commonly. So those two sites are quite common when you're doing performance analysis. Like, hey, is my code aligned? Or what is my compiler outputting? Why is my compiler outputting like no vector instructions for this? Turns out I'm dumb, and I didn't write my code properly. So you can see like in uops info, you can actually find a lot of information about what ports are my instructions running on, what micro operations actually exist in my code. Are they getting macro fused? Are they getting micro fused? Where do they get unlaminated? What happens in those instructions? And Godbolt will give you the assembly that you want to actually run for that. If you're doing the Godbolt to uops info, then you want to make sure you only take that loop part, because uops info will just run the loop without actually calculating what the loop actually does. So you just need to make sure that you're actually passing only the loop part. Do not pass the whole function. There's like some prelude and postlude of the function. You don't want to take that. You just want to take the loop. Other things you should note, well, in some CPUs, you want to optimize for the loop string detection. Not in the Skylake, it's gone. And in Zen 4 removed theirs. But you might want to optimize for that. You want to know the sizes of these. If you're bottlenecking on one of those, then you go search up that size and you go, oh, I'm screwing myself over, and maybe there's a bottleneck somewhere before and I'm filling this up. So you can figure out what's happening there. Branch order buffer. You don't want to take too many branches. You're going to run out of branches to keep track of. This has only 48 entries. So if you somehow decided that you wanted to dump, like, I don't know, you need to like just repeatedly branch all the time. Like, I don't know, if your switch statement somehow decompiled into a bunch of if statements, then I guess you can cry, because that's what's going to happen. Your branch order buffer is going to kill your, it's going to just stall the entire system because we can't do anything anymore. Match statements in Python are if statements. Rust. I'm not a Rust user, I use C, but if it's an immediate operator, like an immediate value, like an integer, it will, in theory, always compile to a switch statement. LLVM will do that for you. But I wouldn't know about, I don't think structures would work for that. Right. So yeah, and then this part becomes less interesting for you guys because most of the time you won't fill out all of this information for like the rename and register allocation table. I mean, I have never seen someone actually bottleneck on that. Well, this one is technically a bottleneck just because the speed you get between rename and reorder is going to be 4 micro operations because the register allocation table can only do 4 renames at a time. And so that means if you have a UOPS cache pushing in 6 micro operations at a time, then you're going to stall on this register allocation table because you're only going to get 4 through. And so this could stall in theory, but if you look at this, like, you can't use all of these ports at the same time. It's really, really hard to do that. You could maybe if in certain workloads, but it's very rare. So for the most part, it's not too much of a problem, but you should probably know that you can only get 4 through on the Skylake. And then the ports is more the issue because oftentimes you'll clobber on the same port. So something like if you have a branch unit on, like, I think it was 6, then you also have like inter operations, right? So if you have 4 inter operations in a branch, then they'll both act on 6 because inter operations are all on all ports. So you could wind up clobbering those 2. And so if possible, maybe you could like pull one off and not do that, try to figure out a better algorithm to do that, or just, I don't know, you'd have to really play with it. This is, most of this is an art of like just throwing things at the wall and praying to God. And then the other things, store forwards don't store and then load it. I really almost never see a case when you want to do that, but I've seen it happen in code before. And so if you have a store and a load, you're going to stall between this store and load, and you're going to take multiple cycles, and you're going to block up on these ports. And then just make sure your caches are set, and then that should be all fine for performance-wise. And then I'll take questions before I talk about more crazy stuff. But yeah, that's like the main part of the CPU. The overview, yeah.
For those like branch misprediction, right?
Yes.
It flushes any instructions, like if it mispredict, right?
It, in theory, should only flush instructions related to the mispredict,
Yeah.
but it could also just flush the entire CPU.
Oh, okay.
Yeah.
Wait, so if it, whenever it flushes like instructions, so let's say it's like the level how does it know how many instructions to flush there? Like,
The branch order buffer.
Oh, okay.
Yeah, the branch order buffer will tell you a snapshot of what happened, and it will be able to use that to figure out which registers, architectural registers, are not useful and which instructions are not useful and remove them.
Yeah.
Yeah. Any other questions? No other questions. We're good, apparently. When did they cook this up? 2015. Well, that's when it released, Skylake. But the main Haswell was their microarchitecture, which this is based on. So I guess you could say it was cooked up before that. Yeah, yeah. Like this is already complex for my brain, and this is just every single piece of this explodes, right? Every single thing here is like a PhD. And like I don't know any of it. I just know the overview. This is just like bird's eye view. Yeah. So, because this is like most of this knowledge is just like preliminary knowledge because I don't have any electrical experience. I don't have any like experience with like ASIC or FPGAs at all. So yes, that's why I know it. Yeah. If I knew more, then I'd be an electrical engineer. So are we good on this? Because it's really big and I'm not sure if you guys got it all. I'm not going to be explaining new stuff. I'm going to be using this stuff. Okay. Yeah. Oh, no, we're like on the end side. We're on the, yeah, we're on the ending side. If you want the muffins, you can. Yeah, you guys need calories? I'll put the muffins here. You guys can figure it out. Oh my God, I missed the stack engine every time. Oh my God. Well, I'll explain it later. Every time I do this. Sorry, I was zoned in. I was zoned in. Yeah, it's mine. Yes, sir.
That's mine over there.
Yeah, Nick sucks. Yeah. Yeah. Yeah, exactly. That's why I was like, no one learns comp arcs in. That's why I was like, no one learns comp arcs in comp sci. Where did I learn all this? I just learned it. I read the documentation on Intel. Yeah, it's like 5K pages. I spent this summer reading. That's what I did. Yeah. These diagrams are on other sites. I have them linked on my on the YouTube channel, but I can write them out for you. I just started. Well, I've been going for a while, but I keep deleting the videos because I'm like, this is not good enough. Okay. The other ones are okay.
I know about the pipeline, nothing about
What'd you say? Intel specific? I'd say most of it is pretty generalizable. The naming will be different. Yeah. But yeah, if you go and read like the like ARM Cortex like 53, for example, you'll see a lot of the same things. Yeah, that's the crazy thing to me, because I'm just like, what?
No, I think they mentioned it once, but I didn't know. I didn't know. I think I've heard of this before, like the algorithm.
Yeah.
But I didn't know about
Yeah. Tomasulo. Yeah. Yeah, that's the one that extends on top of a scoreboard.
Yeah.
It's very similar. Those are the main sources that I used. Yeah, chips and cheese. Yeah.
Oh, that's your channel?
No. That's my channel's name. Overcurried. Yeah. I used to do a lot of Haskell. I did Haskell for like 2 years until I was like, the performance on this is kind of bad. I'm not done with FP. I just like, I rotate. Yeah. Because it's like, I spent 2 years in FP and I was like, I don't know, man. Yeah. I like to see the computer actually do things.
No, but is there anything that you enjoyed with FP?
Simplicity. Like I don't have to think at all. When I write code, I just like, I need to do the thing, and then I write the thing and it happens, right? And then I realized that there's a lot more things happening and I was like, but like, it's very good for prototyping. Like I love it for prototyping. And then other things is like being able to reason about types, right? Like it's like, oh, I know this thing has, for guaranteed, this thing will do whatever I want it to do, and then I just run that thing, right? So,
Do you know how compilation works with functional? Okay, that's a really bad. It's actually really bad. That's why I thought I did, but it was the multiple.
So yeah, they are actually very similar in terms of the first half, right? The first half was the file, Lex, tokenization, parse. Last half is very different. So first thing, functional programming language often have a runtime, which I didn't talk about. What? Like a VM. Some actually genuinely have a VM, like what was it, Erlang and whatever they use. Beam VM, right? Yeah. But things like Haskell compile down to C. So how that works is you'll create like functions and structures that you'll call to generate your like actual function calls, right? So in the Haskell compiler, you have multiple IR stages, a lot of IR stages, and then once you output and run the code, what's going to happen is you have this, the heap will act as the stack, and the stack will generate a bunch of Lambda functions inside of there. And every function's a Lambda function, and you'll generate like as if it was a stack. And then if you want to pass data, you'll have like data entry flags and a structure that points to other things so that you can pass in multiple parameters. And then you'll probably remove a lot of currying in the actual output because, currying's a nightmare for programming. And you'll do all sorts of different things about like, it's a lot of memory. A lot of stuff has to do with how you organize your memory to make it run fast, because you have to do things like tail. Yeah.
If everything's on the heap, doesn't that affect performance?
Heap and stack actually genuinely are pretty much the same, other than, yes, that's one lie that they tell you. Heap and stack are super different. They're so different. And then you realize that the heap and the stack are both on the RAM. And the only benefit that you get from the stack is that you have compile time understanding of where things are, right? That's the only benefit you get.
They say like all like fragmentation.
Yeah.
Fragmentation is bad, but that is not the cause. That heap is not the fault. It's C++. C++ is at fault because you generate 30 objects in the heap, and then you delete a couple of them, and there's fragmentation. But if you created one array, and you allocated all of them in that array, and you stopped freeing them in the middle, and you just moved them down yourself, no more fragmentation, right? So it's the programmer's fault, right? Yeah. If you want to know more about that, you should look into memory allocation, things like memory arenas, bump allocators, heap allocators, and there was one more, but I don't remember.
Wait, isn't memory allocation handled by the OS too?
Yes, but the management and the storing of where is everything in the heap is up to you, right? malloc is you, right? So malloc is just C code that does things, right? So you could write your own malloc. Right, and that's what I often do. Yeah. I write my own allocator for things because, like, if you're doing string stuff, right, you'll often find a lot of people, they'll create a string, and then they'll copy the string, like a part of the string, and they'll allocate a new string for it, right? I want to do that, but I don't want to actually copy it, right? So I think I create this thing called, I create a thing called a string pool, right? And then I use sections of that string pool, and I use pointers into the string, and then a length, and then I just store all the strings in the same place. And if I want to free them all, I just free. All of it's gone, right? What'd you say?
You know, like HRT,
No.
Hudson River Trading. Okay,
I've heard of it. Yeah, yeah.
I think in their interview, they asked me like,
Ooh, that's fun. That's fun. That's a long interview.
I don't know
Then.
if you write it.
I think it's just system design.
Okay. That's a little easier.
Yeah, I've watched a video like I think it was like Sleeping Con.
Yeah.
About like different types of memory allocators. Because I was just like, I thought it was just like basic, like like the free list algorithm. Like
Free list is the common one. That's the heap style. Yeah.
Like I thought it was just mainly that, but I didn't know that like memory allocators can be like different for depending on whatever.
Yeah, depending on what you want to do. Yeah.
So I guess then with Haskell, it's like it would be different.
Yeah, exactly. That's why Haskell has its own memory allocation format, right? Yo, that's fire. No one commented, right?
Actually, well,
Dean?
you know what? When's muffin time in the chat? You know what?
Dean's number one commented. Let's go.
What top fan? We're in top chat.
Top fans.
Number one fan.
Literally. Is this like the damn.
Get it, play together.
That looks so Unity, you know? Huh? It looks so much like Unity.
It is unique.
I knew it. There's like there's a tint to everything.
I think. Yeah, but they said they were having
They're having too much fun.
yeah, they had too much fun making some songs. That's why it came out so late. That's what they said. Yeah, they said that their budget was big enough so that they didn't have to care about when they released it.
I saw
Hey, that's valid though.
I saw memes that like Hollow Knight and all the spin-offs came out when Trump was in charge, and then there was Biden, and then Trump was delayed, and then Trump's back.
Yeah.
Suck song.
No, that's sick though.
Yeah, that is sick.
That's
That's the ideal workplace. Yeah.
No, that's sick though. 'Cause that's like sweet.
Literally.
Instead of like every AAA sucks.
The worst part about AAA is it doesn't even run on my computer anymore.
Every AAA.
Well, not every like some are okay.
Well, so like Concord, Big Classic, they spent so much money on that game, and then they took it off the store.
That's why you need to get indie games.
Oh.
Yeah, I don't know. I can't run any AAA games anymore. My computer's too old.
I think the last AAA I enjoyed was Baldur's Gate 3, probably.
Okay, no.
That one barely runs for me. I get like 30 FPS.
Oh, yeah, that's fair. Yeah, my computer also had a bit of trouble running it.
Yeah.
Yeah, that's the thing. It's just making better graphics, and sometimes it's not even better, but it just runs nice.
That's the best part.
Like, it still looks good.
Just a little blurry. The shadows seem to like be ghosting. He doesn't care about ESD, okay?
Like, stop hitting the PTV, bro.
His laptop broke. Nick, Nick, where was the washroom? Straight this way. Oh, between the stairwell, between the stairwell.
I stunk so bad.
Stairwell moment.
Join the Minecraft.
I literally, every time I explain it,
Yeah.
it's not even that hard. I guess it's right there. Like, what is wrong with me? I don't think I missed anything else. It's always the stack end. What? Oh my god! What? Zero and yeah, I need to talk about that. I'll talk about that. Every time. Those parts right here. It's the bottleneck area. When I get to the bottleneck, I'm like, brain off. No, screw the stack engine. No one cares about the stack engine. All right, I'll say those things later.
I'll be leaving this place in a few days. Leaving Ottawa in a few days.
Where's Nokia?
I'm going to Montreal for a trip.
Oh, I see. Fun.
Tori legit just called me. He was like, let's go to Montreal. I was like, okay. And then he hung up. What the fuck? He's like, all right, we booked the hotel. It's expensive. It's expensive.
So bad.
I was like, holy shit, bro.
So I guess you're going to Montreal now.
I'm going to Montreal.
It's very sad. Very sad.
No, not sure. Rage kill?
Are you winning?
Looking good.
Oh shoot, you are.
Rocket Cycle. Oh. Me, Becca? Becca? Oh, Rage. Rage Instant was probably worth it. Oh, imagine that's too early. Actually, low key, you low key threw, bro. No, it doesn't count. Okay, wait, I just want. No, 3 seconds. Okay. Wait, that was close. No, I want to have killed. No, but like the whole part, you actually almost lost. Dude, it always gets an upgrade. Oh, damn. Bro, it's like when it gives you gold, it just sucks. What are you gonna fuck do?
No. Bro is poor.
Bro is poor. Is it net?
Negative 30.
I owe you money.
Euro.
Bro, you say you want to buy something. What are you gonna buy with $0? Don't worry, I'll buy it. He's got organs. He's gonna pay with his hopes and dreams. Bro, I was coding my
Yeah.
when I change states, when I have to change out the menu pointer that they're pointing to, because like when you press one, it's different depending on the state. I don't want to do that. Like I don't want to be changing. There's no better way to do it.
You know.
You like how much money I have?
64 cents?
What can you buy with that?
Dude, you're literally I'm so rich, bro. I'm so rich. I know.
Yeah, I've got a stack.
Can you even buy anything?
That's more than 63 cents.
Just go back in time.
Nah, I think it can get you a house.
Oh yeah, definitely. They give me a house. Yeah, you just have to build it. That's all.
It's made out of cardboard.
Free house.
No, I'll be considered a slave.
But think about the inflation. The benefit. Money would go so much. The camera sucks.
Yeah.
That's true.
Mine sucks at focusing too. We have the same.
Linux is pretty cool.
It's cool, but like,
It doesn't work.
does anything work? Like,
You're right. You're right. That's correct.
that's the thing. Like, everything is just like whatever. There's no standards.
Yeah.
That's the best part. Everything.
Linux has no standards. Windows has no standards, but it's dying. They're the hardware people. They're the hardware people. What do you mean? Of course they have standards. The software people don't have standards.
We need to kill all
Dude, I just like joined a business degree. Kill all software.
Stop killing. Not the software, bro. The engineers.
Start killing games.
Start killing games. Yo, guys. It's a publicity stunt to make people trust software more.
Exactly.
There is no big software.
So bad.
There's a bunch of small software. Best software engineers worked on this. You can trust our software.
Their best software engineer is someone who graduated from Carleton.
Yeah.
Like,
Best software engineers.
Accidentally. Is this an story?
No. I mean, that's like my. Well, my so
yeah.
I said it's 5 people, like 2 like actual like people, and then 3 small. One of them.
Yeah, they're not people.
No, they're not. They're not. And then like, I said 5. More like 4 because our supervisor doesn't code.
Oh, it's a 5-coder.
No, he supervises.
Well, yeah, but he also just like does all the meetings and stuff.
Yeah, he supervises.
You know, yeah.
Which explains why the website sucks.
Is it better than Carlton Central's website? Yeah.
Yes.
Okay.
No, Carl.
I don't know how they made the links different sizes. That takes effort.
Hire literally anyone at the school, bro.
People at the school will do it for free.
Nick, didn't you say something about like how you can do like a JavaScript plugin onto the Carlton
Yeah,
website?
Yeah.
I don't know if it's gonna work though.
If I could just like query all of the courses and then just like inject my own JavaScript.
Oh, that's true. But then you wouldn't even need to do that. You would literally just ask them, "Hey, can you just hit F12 and copy the thing to me?"
Yeah, it works either way.
They should hire the people that designed the EXM website.
Mm. The School of Art.
Bro.
They're artists.
What the fuck is this? It's Yale School of Art.
Yale knows what they're doing. You don't understand.
No, they don't.
The white area. The white area.
Down the hall.
Yeah, straight white. Okay.
Wait, which
What?
Docs did you read? Like,
Which docs? The Intel optimization guide, the Intel software development manual, Agner Fog.
Intel software development manual. Is that like so broad?
Yes. Yes.
So you just read it front to back.
No, no, no. Like you're not supposed to read manuals like that. You just jump through and you find the things that are relevant. Yeah.
yeah, that makes sense.
I'm not gonna read the 6,000 pages.
Did this all this time.
Yeah. Yeah.
You get the extension?
What'd you say? Yeah, yeah. I got an extension. Yeah. Curtis Wright. Curtis Wright.
The only issue is like,
Oh,
Yeah.
somebody has to off the giant restart.
should apply to these like these small companies.
Yeah.
Find like headshots and shit.
Yeah, I want to, but they don't accept me.
They don't accept you.
They don't take me.
Why?
Yeah, yeah. I'm trying.
Are you going to hack yours?
Hack North, nah.
It's like sneak onto the bus.
No, don't. It's like too much. That's not pretty.
No, just go.
8-hour drive. And if you're gonna get kicked, what if you get kicked on you in Peterborough?
They're just stuck there forever.
Legit, it's like come to hack the North. How can you want to do it? It's literally just like raise up. Only just talk to the like HRP and they'll interview you.
No, I
My
was
life will interview
just
you.
keep, like posting on like YouTube or whatever, and then just like yeah.
Yeah,
Like,
yeah.
it's like ironic. Don't delete your videos.
Yeah, yeah.
Because like maybe until like 2.1 like Intel literally like engineers really bad. But for everyone else, that's just like kind of cheap.
Mm.
Like if you like delete this video, like I might find you and like.
All right.
Also, what's that HU component? I just realized.
HEU is the address generation.
Oh,
Yeah.
Like, it like raises the metric.
Yeah.
I think.
It just calculates based off of the registers where you're trying to access. Yeah, and then also just stores and stuff.
Wait, I've been running that.
You don't get any.
Yes, yes,
On like bitwise.
yes, correct. Yeah, that should be all. Yeah.
Also, like, I can give you a couple of examples of what that within the complex. Like, do you have any more examples of it?
For example, add with carry or vectorized move. Those are the two ones I can remember that will get decoded in there. Yeah.
This is like the NP vectorized move, right?
Yeah. Dude, the vectorizer is so stupid on like the compilers these days, but like it's hard, right?
Yeah.
But like I wrote an example once where like I did this. So I had this this older coworker show me like a hex conversion algorithm where you just take like the bottom nibble, right, the 4 bits, and you just use a lookup table, right? So I was like, okay, I can use SIMD to like look up, right? So I wrote one where I use branches, one with the lookup table, and one with AVX2, right? So that's like the 256 size, right? And then I forced the compiler to generate 256 size for both of the lookup and normal. And then I ran it and I was like, I looked at the Godbolt output and it was like a full like double page of like just for the branched one. And I was like, it ran faster than the lookup, right? Just because of like stalls. But it ran like maybe like 0.1, 0.2 slower than mine, which I didn't optimize at all. I just wrote the dumbest code possible. And I was like, what? I tried playing around with alignment, but I don't think it's that.
Also, like, I don't know. I mean, that taught me about like branch programming in first year.
Yeah,
I didn't know that it would like actually make like a significant difference.
it can make a difference, but if you use it too much, then it makes a negative. Yeah, because the thing about branchless is what you're trying to do is you're trying to calculate both at the same time and merge them somehow, right? So you can use predicated moves, or you can use like multiplies, which I'll talk about. Actually, I forgot to talk about that, but I'll talk about that. You can use multiplies to do that, or something like that, or bitwise ands or something, right? But the thing is, you have to calculate both sides. So all the micro operations that have to run, both of them use double it, right? But if your branch mispredict happens a lot, that double stack might be like 8. But your branch mispredict is like, look at how many steps in there. There's like 15, 19 steps, right? So you miss like 19 cycles, right? So depends. Yeah.
Me and Alex waiting a couple times. Oh, you did? Well, you know they're adding. Oh, yeah.
Stone. Yeah.
You can know all this, but if you don't have the union find template memorized in
Oh, then you're not getting a job. You're not getting a job.
you can just shake the cup.
Yeah.
Oh no!
Dude, union find is actually so like brain like heavy too. Like I forget it every time.
Union by
Yeah.
passive pressure.
Yeah. All of those suck, and I forget all of them every time. Yeah. Meanwhile, for this one, it's like it's kind of obvious when you think about it. It's like, oh yeah.
It's obvious.
Well, no. Once you learn it, once you learn it, you're like remembering this. Like I'm not going off of a script, right?
Oh, because like that would be like a natural.
Yeah. Because you look at it and you're like, obviously it has to do that, right? Yeah. Union find is like there's some formula and like you just know.
Oh, they just screwed them over.
It's fine.
I think it's gonna be great. I can't wait for September 9th, Andrew.
Oh, that's not that far away.
2x
Wait,
KO.
that's so soon. Yeah, it's crazy.
I want to take that game seriously.
He's gonna be grinding.
I'm gonna save it.
I sweated in a fighting game or not, like a year ago. I got good at it, but I hate it.
I'm hoping I can win a fight.
I mean, that's valid though.
You know, it's great to us. He'll probably gonna get a gotcha mechanic.
I can't wait.
Oh, they actually have an offline mode for character managers where every character's on that. Which is like, that's so good. That's so like consumer friendly, bro.
Yeah, that's pretty cool.
That's so good. I can't.
He's waiting.
I'm gonna be goated.
I still don't understand how we ended up having a gotcha system. Like, that's so stupid.
For the champions or
For the skin.
Oh yeah, they did that recently, right?
Yeah, it was recent. Like, they started this year. And like, to be guaranteed the gotcha, you need to spend like $200.
They need more money.
No, because the post costs so much. It's not even worth.
That's
They need more money.
that's actually.
I mean, if they give us interesting content, then sure, like the whales. Well, I mean, they're still like, to be fair, they're taking advantage of people.
Yeah.
Yeah.
To be fair, at least it's not like. At least it's only cosmetics. Sure.
No, but
At least you know you're not gonna get any money back.
is they're downgrading their cosmetics because they don't want to put it. Because previously they have like legendary tier skins, which they sold for like I don't know, $20, I think. They're too lazy to make the actual $200 skins they're selling actually good, so they're downgrading those to legendary quality and then downgrading legendary quality to lower quality. So they're just downgrading the quality overall, which is just
They're
frustrating.
geniuses.
Which is just frustrating. Better than the fighting game space is awful.
It's like you paid for a full price game and have to buy DLC still.
Yeah.
And it's like.
I want to play the game and I want to play this character, but it costs money to play that character.
That's me. I just stopped getting the Street Fighter season passes and I just got a lane. I don't even play that much.
Yeah. Valid.
Grand Blue though. I own the season pass, but I realize I hate the game.
Grand is go.
They're making a second.
Have you seen Grand's grab?
Second EX characters. They're all worse than the original.
They're EX as in extra stupid.
No, the whole thing. I think Vegeta EX, but their whole gimmick is they just do more damage than the original. Dude, it's insane. The last 3 characters like do so much damage if they get the right hit. like it's insane. They like too touchy. And
Is
like
it power creep or just like a different?
it's not power. They're worse.
Okay.
It's just like they're more inconsistent, but like if they get the right hit, like if you do something right in the middle and fuck up, they will make you
It's
they'll
for,
make you remember that mistake. You're like,
it's for that 1 in 100.
yeah, pretty
Actually,
I just like okay, no, actually the new character wellness is like I blew you.
because it was like a 5-minute walk.
I can't
And
lie.
now all the
I thought it would be hard at first because he has single hit confirm, so you can't like press the same button for like all of it. But he is for actual apes.
the best way to read
He does like mad damage. He has a move where he just like goes forward from full speed and then hits a needle you and is plus on block. So he's like all right, I'm gaming now. And he has a move that's supposed to be like you can do it on your block and then you're supposed to be able to hit him.
Dude, he's
back
playing
for
the
it.
same board. It's so bad. How did this guy make it?
But it spaces out at the worst upper range that nobody's buttons that would actually come out in time reach him. And you have to like
Like, look, watch the
forward for
band.
like a frame to walk forward and then press the button right up
Bandit.
with like straight. Oh my God.
The bandit just killed like something. Like, look at the bandit go. It's done stupid. That came over.
It's a, yes, it's the burning cat gif. He's wide. Compiler intrinsics, yeah, that's how you do SIMD.
How do you do sort?
That's how you do SIMD. You just have to use intrinsics.
Oh yeah.
Yeah.
Because you can't do that in C or just like regular C.
Yeah, because you want to emulate an operator, like a plus operator, right?
Yeah.
Well, you can't because that's not in the language specification. So you have a library that'll do it, and the compiler will know what that library wants you to do.
Oh, it's like you can call like specific like instructions in like C.
Yeah, so like you know how add produces binary? So vectorize add also produces binary, but you don't have the symbol for it. So you have a function for it. Yeah. All right, are we ready? We're good? No. Nearly, almost. Maybe like 30. We can go to Chinatown after this. Yeah. Okay. Let's talk about this. So I missed a couple things by accident. Just like some minor things that I always forget exist because I don't really care. And then when I find out, I'm like, oh, right. So there's one thing here called the stack engine. The stack engine's job is to check this output of the decode set, this legacy path. This is called the cache path. The legacy path is over here. The output of this, we're trying to find out, do we have like a push? Do we have a pop? Those two instructions modify the stack pointer. And we want to be able to say, okay, well, if you're modifying the stack pointer, I'm not going to wait for you to go through the whole entire chain here to find out that the stack moved by 4 down, because I know it moved by 4 down. So I'm going to keep a counter here that tells me, okay, so how far up and down am I relative to the actual stack pointer? And the moment I run out of, like, when my counter saturates, I go, okay, dump a UOP into here that actually updates that stack pointer. Or if an instruction comes down that says, oh, read the UOP or modify the UOP, I'm going to dump a UOP in and modify it for them so that we can keep it in sync and we can also reduce the latency of it going all the way through, right? The other thing that I forgot is optimizations inside the decode queue, or I guess the rename part. So after decode, we also have this idea of move elimination. So obviously, as you know, every time we modify a register, we make a new register to save it in. So if you're going to move a register to a new register and then copy a register to a register, why would you make a new register when that register is always going to be the same? So you're not going to do that. So that's move elimination. The other thing that you're going to do is you're going to say, okay, so there are some common ways to zero and create zeros or ones inside of your registers. Common ways, for example, XOR register with register. If you take XOR 1, 1, then you get 0. 0, 0 is 0. Obviously, that makes all zeros. So if you hit this stage in the pipe, you go, well, I know it's 0, so I'm not going to go and calculate it all. I'm going to go and just make a 0. Same thing for ones. So that's very common when we want to do things like remove dependencies. If you have a register usage, like a partial register usage or a 32-bit register usage in a 64-bit register usage, then what's going to happen is that this part of the register needs to get updated when you modify a 32-bit, right? So you have a 64, oh my God, running out of space. We can remove this now. If you have this part of your register, and this is each 32 bits, right? And you want to modify one part of this, then you actually need to have this part copied over at the end when you modify that piece of the register, right? And so one common way to reduce the stall between that is to XOR itself. So you remove this and you produce a 0, right? And so you don't want to wait for that whole thing to happen because then you're going to get another stall. So you 0 it, and then this part right here will go, okay, we're going to use a 0 idiom and then not execute it. And we're just going to know that it's 0. So that way we can 0 it right here, and then we can say, just modify that part. And you'll find a lot of newer instructions. Sorry, I said this is 32-bit, but from what I remember in 32-bit, when you move a variable in to 32-bit land on a 64-bit register, which most int registers are, then what's going to happen is it's actually going to 0 it out for you because of this dependency issue. But if you're not doing that sort of thing, then you're going to want to 0 it out. So for 16-bit to 32-bit, or if you're not moving into a 32-bit and you're doing an add or something like that, then you're going to want to do something like that. The other thing is that when you want to 0 or 1 a register, and you don't want it to go all the way through, the other purpose for that is like you often have a register that sets to 0 at the start of your loop. That one also is going to go here. Very useful for reducing the amount of instructions that have to run through the whole backend. So very cool. Anyways, I do want to talk about a couple optimization techniques that we use, and then I'm going to talk about usage of this thing in a bug. I guess it's a bug. We can call it a bug. We found not too long ago, a few years ago, that we patched. Thank God. So first of all, we're going to start at the top. The L2, L1, and L3. We don't want to thrash our cache. We don't want to screw it up. So we don't want to use linked lists. If you use a linked list, chances are you're going to be using more memory than you need to be. You need to store a pointer. You need to store a value. And for each value, you need to store that extra block of data. Second thing, linked lists, sometimes if you allocate them improperly, they will be in different parts of memory. That means you're going to use different cache lines. That means you're going to go and repeatedly fetch from L1 to L2, or I guess from L1 to L2, and then over to L3, right? And you're going to be repeatedly doing that. Sometimes you even go out to RAM just because of how sparse your data is. And that's memory fragmentation that some of you have been talking about. Other thing that you don't want to do is to force cache lines to be loaded repeatedly. So I see some people misuse SIMD, and they'll try to load everything at once. And then, so you'll load all the cache lines, and then you'll do operations between them, but you don't actually need to do all of those. And like you wanted to use some parts of the structure, but you didn't want to use other parts, and you'll be loading too many cache lines. That's going to be the same problem. So sometimes when you create a structure of arrays or an array of structures, you need to understand what the actual access pattern of your data is. Do you want an array of all the reds, all the blues, and all the greens for your image? Or do you want an array of red, blue, green, red, blue, green, red, blue, green? And that's going to depend on how you're going to use the data, right? If you're going to use the data in a way where you're not actually going between the red and greens, and you actually want to actually pack them together, well, then loading 3 cache lines every single time throughout this is kind of useless when you could just load it all in one go. And the predictor will be a lot happier because here's the thing. We have hardware predictors in here. So long time ago, we had software prediction where you would, you'd be like, okay, so I need to load some data. And I know it's not in L1 because it's probably not going to be in there. I haven't accessed it in a while. So I'm going to pass this instruction through that's going to say, okay, I need to load a cache line into L1 that says, that holds the value of the start of my array, right? So I'll pass an instruction to go through and do that. Nowadays, we don't really do that because predicting whether or not it's in the cache or not is like really, really hard. And you're sitting there like, I don't know if it's in cache, and where do I put it, and how do I make it load the next one in the next part of the loop or something like that. So what we'll do is we have hardware prediction methods or hardware prefetching methods that will go and go, okay, so if you access a cache line and you access the next cache line, well, then you probably want to access the next cache line after that. So we're going to prefetch that cache line from L2, and L2 is going to go grab it. And L2 is also going to do prefetching, and it's going to check for certain scenarios like, are you repeatedly hitting the same cache or same cache area, the same cache set? So a set is going to be like a specific mod of memory. So if you're always hitting the same cache set, maybe you should start doing prefetches. Because one thing about always hitting the same cache set is that you have only a certain number of lines inside of a set, and you have multiple sets in here, and each set is a mod of the actual total memory, okay? It's not too important, but just know that if you hit a specific multiple called the critical stride of when you access your array, very common in memory matrix transposition, when you access across rows, you might hit a critical stride where you have to keep loading into the same cache line the data. And what's going to happen is, because you keep loading the mod of the data, that means eventually you'll fill up that cache set. And then you're going to start removing things from the cache set. So you remove all the data that you wanted from the cache set. And then when you go back to the top of your matrix to do another transposition, you have to do it again, right? And so you throw away all that work that you did. So some things we do, tiling. Some of you have heard of matrix operation tiling, where we tile a section of the matrix. So you'll have, you don't need this. So if you have like one value, if you have like one spot in your set, right? So you have your sets here, right? And this is all your memory, and it's a mod of it. If you get a specific stride, you can hit the same set every single time you access data. If you access this spot, this spot, this spot, this spot, because it's a specific mod, so a multiple, right, will hit a specific set. And so if you only have one level of associativity, one data or one line in a set, then what's going to happen is when you access these parts of your matrix, you will throw away that line every time. And so what we'll do is we'll access, in this case, tiling wouldn't help a lot, but let's say you had 2 levels of associativity. Then you could access this line, and then proceed to access these 2 parts repeatedly. And then you can access these parts here, right? Now you don't have to do a bunch of like throwaways of the cache or as much throwaways. And you basically reduce the strength of how bad the thrashing of this cache is. The other way that I've seen in older programs is that you'll put in a specific prediction that I want to load this next line in the next run. So let's say I'm here and I want to load this line, then I load like the future iteration 4 ahead, and then like it's a lot of pain. And also it takes a lot of time and you have to go through the whole CPU system. So often you'll find tiling is generally better for spreading out the damage of this. But there is some overhead for tiling, which is just for loops. Multiple for loops will just clobber the ports over here. You only have 4 ALU ports. So if you're doing a bunch of for loops inside of each other, you'll fill up your ALU ports and you'll use up a little more time. But the damage that happens if you hit that critical stride won't happen. So you become a little bit more deterministic in the actual runtime of your code. You can actually figure out more. Is there anything else that I want to talk about? Yeah, we can just a small word about vectorized operations. I'm just going to say it again, right? Vectorized operations are not deep, right? They're just the idea that you can store multiple registers in one register, so multiple size registers, and you can do, well, first of all floating points sit inside of the vectorized registers, but the other thing is that unless you're using x87, which I hope you're not using, your compiler won't output x87 these days. Your vectorized registers allow you to operate on a lot more data at once. So if you have a vectorized register that holds, let's say, 8 integers, then you can do 8 adds all in one go, right? And so you'll find a lot of the times when you're reading code, you'll find the output of the assembly will be like v something, v move, v add, v whatever. And that's going to be the vectorized operation on these registers. And the types of registers you have are called XMM, YMM, ZMM. That's just, I guess we're great at naming things because they don't mean anything. XMM is the smallest size other than MMX. XMM is the 128-bit, I believe, and then YMM is 256, and we doubled to 512 in AVX 512, which has been disabled in a couple CPUs recently, but it's pretty useful. The issue with AVX 512 is it takes up a huge amount of space. So one thing you should know about AVX 512 is, well, I don't have the CPU die here. This part here is like way bigger, but AVX 512, if you had an integer part of your die usage here, like this is just all of the ALU, well, if you had an AVX 512, it would just be like this, right? It would just be humongous. And so one thing Intel did is they turn off AVX 512, just like they turn off these this legacy path if it's not running. So AVX 512 actually has a startup time. And so if you're not using AVX 512, and then you're planning to use AVX 512 in the future, you probably want to start an AVX operation and then let it warm up and then have it run. You have a question? Okay. So when you want to run AVX 512, just make sure you have the warm-up time if you're on Skylake. I don't know about the other CPUs, but that might be something that you consider because most people want to turn off that huge amount of vector space if you're not using it. And so that's why you should probably take advantage of the AVX instructions, or at least the vectorized instructions, when you can for high processing power, because you're wasting like a quarter of your CPU just doing nothing, just off, right? It doesn't do anything at all ever, right? Which is really cool. And I love it when I see code that doesn't use any vectorized instructions at all. It's very awesome. Yeah, and you can often use, if you think, when can I use this? You can use it in math, and you can use it in strings. Those are the two most common places I've seen vectorized operations, math and strings. Yeah, so just keep that in mind when you're going about this. Yes, yeah. Yeah, yeah, it's parallelized. Yeah, and to do that is very, very hard sometimes because you have an algorithm where you have like some parallel work right? You want to like, I don't know, you want to do something across 4 of these. Well, that's fine. But what if you wanted to do across like a different set of those, right? If you wanted to do something horizontally across these blocks, then what would happen is that you'd have to do a horizontal vector operation or serialized operation. Serial operations are like the bane of like SIMD, and also any parallel operations like multi-threading, which I didn't even talk about multi-threading because I'm not going to touch that. That's a nightmare. I'll touch on it, but no, yes, technically, both. Like the code has to use the core, so yes, it would be the OS, but the core is the one threaded, so both, yes. But yeah, when you do vectorized operations, it's often a pain when you have a serialized operation, and so they often have certain things like, oh, you split the register in 2, you move it over halfway, and then you do a merge, and you do like a sort of log n merge of all of the operations that you want to do. That's a common way to merge SIMD operations, just so that you can know. It's not too important. You'll find it out if you actually get into that area. And if you don't, well, then it's fine, whatever. But yeah, the other thing is caches are a nightmare. Caches have been a nightmare since the beginning of programming. I don't know if you know the saying, but there's this old saying, I hate it, but there are 2 hard things in programming and computer science: naming things and cache invalidation. So one thing is cache invalidation sucks balls. We have 1 core. If these 2 cores decide to interact with each other or on the same memory, how do you make sure they're actually the same thing? How do you make sure they're interacting on the same data? And you'll often find sometimes you forget that that's how that works, and you'll leave a variable non-volatile or non-atomic, or either or, right? And that causes a lot of issues when you go into a multi-threaded situation, and then you realize they get misordered, and you get bad data, and then you crash. Well, maybe you don't crash. It's worse. So what happens is if one of these lines is stored in only one CPU, right? If only one of these lines is stored in the CPU, then we enter this mode called exclusive, right? So a line in the cache will become exclusive. And then if that line gets stored by another core, then we remove that exclusive and we call that line shared, right? And then once it's shared, we go, okay, well, if one of them modifies it, then what? Okay. If one of them modifies it, then you call this one modified, and then you call this one invalid, okay? And so at the very start, this one was probably invalid. And then what happens is if this one goes to grab it again, and this one hasn't flushed it to the L3, then what happens is this one will become owned, and this one will become shared, okay? Exactly, yes, exactly. And then eventually, if you actually want to do anything to these guys, you have to flush these 2, and this one would become invalid, and then this one would become either exclusive or nothing. And so this is called MOC. Okay. You'll also find some people, some CPUs have MESI. The Intel CPU uses MOSI for their cache coherence algorithm. And so the way that they actually notify each other, because these cores need to be able to notify each other that things are happening, this interconnect right here will have this idea called a snoop. There's another way called directory-based, but that one's more complex. So we'll talk about snoop. Snoop is when these 2 watch for any action on the L3 bus. When the L3 actually gets activated and says, oh, I need this specific cache line, well, then what happens is this one will try to pull the cache line, and this one will go, okay, let me look at that broadcast. What's going on? Do I have one of those? If I do, tell him I have that, and tell him what to do with it. And if I don't, then I ignore it. Yes, L3 is a shared memory. Yes, yes. It's a unified memory across them. That's why there's an interconnect. Yeah. Yeah. No, it's good. It's good. Yeah. Because I mean, all memory is shared. Yeah. Yeah. So I think that's all about caches, right? That you need to know as a software developer. If you're an electrical guy, I'm sorry, I don't know anything about this. But I do want to talk about the interworkings of this. So if everyone understood the premise of the stuff that I spoke about, then I want to introduce one last concept and I want to tie it all together. We're all good. What are you lost on? Everything? Okay, whatever. He's lost. It's fine. I mean, they were pretty great back in the day until they started not being able to output their 10 nanometer process, and a lot of like the execs weren't able to actually make people do things. That's what happens when you don't have an engineer at the top. Yeah. We need you up there. Yeah. So one last concept. In the CPUs for Intel, a lot of the CPUs have this idea called hyperthreading. And if you hear about hyperthreading, just think symmetric multithreading. Okay? I know it got harder. Okay? I know it got harder. You need to trust me. You need to trust me because Intel's the only one who uses the word hyperthreading. Okay? Symmetric multithreading is just the idea that you take this entire CPU, you copy a couple things like buffers in here get partitioned, or some buffers get copied. Some of the architectural register state will get duplicated, and some of the buffers get partitioned, as I said. So what's going to happen is during this stage, you will get one thread running on the instruction fetch, and the next clock, a different thread will be running on the instruction fetch, and you'll have two threads. Yes. Yes, that's right. And so you'll have two threads in here, and they'll alternate for each of these sections here. And when one of them's off, one just flows through all of them. Yes, it's completely normal, except some things are duplicated and some things are magic. Completely normal. Yeah, so that's hyperthreading. And it's sometimes a good thing and sometimes a bad thing. Hyperthreading is great when you have a lot of I/O operations, because you're going to stall here. So one of the threads would have stalled the entire system, right? But the other thread can actually start doing things, right? So I/O and like stall heavy code, bad code, runs really great on hyperthreads, because that means that all the other applications can still run. So I love hyperthreading when I have bad code. I hate hyperthreading when I try to write good code. Because what happens is I'm alternating between two threads that I thought was one thread, right? So on my CPU, I have a Skylake, and well, it's technically a Comet Lake, but it's just a revision of Skylake. And what's going to happen is I spawn 16 threads because I think that my OS says I have 16 logical cores. Turns out logical cores doesn't mean physical cores. And I spawn 16 threads, and they're thrashing on each other. So I have to spawn half of them if there's hyperthreading. And I just have to know. So that's one thing. If you're writing high-performance code, remember, how many CPU cores do you physically have? And do you want to use hyperthreading or not? Yeah. So there's a lot of bugs around hyperthreading. And it's not because of hyperthreading. It's because Intel didn't foresee a bug, and AMD may have foreseen it or may not have foreseen it, but they happen to have different architectures, and AMD was less affected by this. I think ARM was also less affected by this. And Intel got a lot of damage from this. It was really bad for the reputation, and a lot of money spent on their time and a lot of performance lost. My CPU went down like 5 to 20% in performance like overnight, right? They released a microcode update that just absolutely tanked. Depending on the operation, obviously, things would become really, really bad, especially if you cross kernel boundaries. And so I'm going to talk about why that happened. So a few years ago, this idea came around that we could do something called microarchitectural data sampling. Okay, it's when you sample data out of this microarchitecture because you know something about the microarchitecture that doesn't affect functionality, it just affects the actual state, right? So it's weird. Let me explain. Do you think what's in the L1 data cache matters to the execution of the code? No, that's correct. Functional requirement says that this L1D cache does not need to exist at all, and you could go to the RAM every time, right? It's just a copy. So the state of L1D does not matter, which is why Intel did this one optimization that kind of made this really suck. So when you access memory, you have this thing called protected memory. So you'll seal memory, or memory seal, mem protect, some area of memory to set it to read, write, or execute and remove those or add those, whichever one you want. Okay, the CPU needs to go check that using its, apparently I didn't put the L1 TLB I or BD, and then this one comes from here and this one goes there. It doesn't matter. That TLB there, it's from the translation set, and then there's a memory management unit somewhere. I don't really know where I should put that, but it's somewhere in there. And the memory management unit will do page table walks. It will check if the memory is actually paged in. It will check if that memory is readable, executable. It will check if it's kernel memory. And if it is, then you've just accessed memory that you shouldn't have accessed if you're in the wrong ring state, ring being a permission state, right? So if you're in the wrong permission and you access wrong memory, then the CPU should throw a fault and be like, that was bad. Okay, so it sounds all fine. The CPU does do that, and that's all perfectly fine. But one thing that does happen is that we do out of order execution plus, well, that actually doesn't really matter. We do branch prediction, right? The issue is with branch prediction, we start running things that we don't want to run. Well, then the L1D will start loading things we don't want to have. And then what's going to happen is that we can go, okay, well, if I could somehow conceive of some way to run some code I didn't want to run, and then also affect the microarchitectural state in a way that I can control, and then say, okay, well, now that I have that information, I can go and guess what value, or actually know what value you just tried to load into memory, right? Because you affected some part of the cache system. And so there's been multiple things, Spectre, Meltdown, Cache Out, and other microarchitectural attacks. And they affect things like the store, the line fill, like Cache Out was on line fill and LD. Store buffers and load buffers, I believe, was Spectre maybe, and also L1D. So what happens with this is we can write some code. And it's really simple code. Does a lot of dumb things. So we say we flush, or actually let's create an array. So let's create an array. Don't really know how big it is. Let's just say it's a really, really big array. And then we flush the cache for that array. Okay? Then what we're going to do is we're going to say, okay, now I want to, like, let's say, I don't know, turn off exceptions. Right? I can turn off exceptions. This is one way that you can actually not use the branch predictor to cause this issue. But one way is to cause a misprediction and also do this. So you could say turn off exceptions or mispredict. Then the next part here will be, okay, load into a kernel memory. right? Load some kernel memory. Then what we're going to do is we're going to load, we're probably going to divide our A by like some n, right? To make sure that kernel memory is within our array, okay? And now all I have to do is load the address of A. I guess I should have said like into B, right? So I load the address of A. Now what happens is, because this section does not throw an error, we have kernel memory in here. We know which line broke, and we do a timing attack, which is meltdown. Okay, there are other ways, for example, cache out. If you're using hyperthreading, you can actually pull out of this line fill buffer, but let's talk about meltdown. In meltdown, what you'll do is you'll check timing. You'll check the timing for each of the spots in the array. Well, probably like the cache lines. Yes, either the fastest or the slowest will be the kernel memory, depending on what system you try to make for this. You can make other systems, like slowest is the kernel memory or whatever. But that's going to be the number. The I will be the number in the kernel. And so really slowly, you could do this over and over again and read the entirety of your kernel memory, dump that to a file, and then be like, hey, I have your kernel memory and there's your password, right? So I could make your browser read all of your memory, right? All of your kernel memory. Every single library you load, I could just link them all and then just read them all, right? So bad things happen then. And so what we decided was, well, what Intel decided was, okay, well, that sounds bad. Because we can snoop from the line fill and the store and loads, we'll do certain things like we'll zero out these guys, right? If you enter kernel memory or kernel execution, or you exit kernel execution, the OS writers have to write this command called virw, which we change the microcode sequencer to activate something that will flush these, right? And that way you can't actually start speculating as well. Yes, so you load kern, and all of this will execute, and they'll sit in the line fill buffers, and then you'll flush them, right? So that's generally how they work. Now, there are still issues with that, obviously. You have to write OS code to actually fix that problem. And so AMD didn't have as much of an issue, because when it went out to go get it, it would go see in the TLB, hey, that's not a good idea. And then it would crash. And the reason why Intel didn't do that is because ordering of exceptions is difficult, and they didn't want to make the circuitry for that, because that would either take up more die space or time. So they didn't do that. But now they accidentally paid the price because they didn't foresee this really weird circumstance, and now they have huge performance losses on the older CPUs where you actually have to defend against this. I don't know who wrote Meltdown or Spectre and like all of those, but a lot of security researchers were working on these things. And there was a team that published both Spectre and Meltdown, and they have a site. It's a very cool looking site. Yeah. But yeah, that's the nightmare that happened, and everyone's freaking out over that. But apparently no one knew about this, because I didn't know about this until just like a few moments ago. So that's why you lost performance one day, right? Like in 2019 or something, right? Yeah, so we incorporate the microcode sequencer into our cache section. We talk about pipelining Superscalar out of order, and we talked about the branch prediction methods and mispredicts, and also the mistake that Intel made with exceptions on kernel memory. And so that's the overview, the broad overview of CPUs, just the Skylake, right? I probably won't go any deeper than this. I don't care. I won't learn anymore. I'm going to start applying this knowledge in my field, but I'm going to start learning more different things. If you want to learn more things about this, I have the links on the YouTube channel that you can go look through. A couple names I can give you. the overview of stuff, you can look at like of how to program well. You can look at like Agner-Fogg's stuff. You can look at he does like a bunch of statistical analyses of microarchitecture and sees like, oh, that took longer on this specific size. That means that this is like this is the size of the branch target buffer or something, right? And Chips and Cheese does that as well. Real World Tech and ANN Tech do that. And then you have programmers like Casey Muratori who like has very nice drawings and diagrams on his YouTube channel, and he has a Substack where he talks about performance optimization. And I believe Daniel Lemire, Daniel Lemire is I believe a professor in like Quebec. He created SIMD JSON, I think, which is with a couple of professors and like students, I believe. They worked on optimizing SIMD parsing for JSON, I believe. That was what he did. And so you could look at that. You could look at also Google Highway does SIMD optimization. They have a bunch of stuff about that. Beyond Rope, also known as Travis Downs, talks about a lot of microarchitectural benchmarks that he's done, and talks about the niche weird things about, like, for example, like store forwarding aliasing issues and mispredictions inside of the store forwarding, which cause stalls. You can go look at on Stack Overflow. Peter Cords is a very, very common name that you'll find if you start looking into this stuff. Every single answer, I keep seeing him everywhere. He has a lot of answers on Stack Overflow for a lot of these things that you may be interested in. He'll give you the history and all the performance implications, and it's really cool. And the Intel docs and the AMD docs are really great. If you need anything specific, you should go look at the table contents, jump to the spot where you need it, and you'll find a spot that says, oh, here, it actually turns out the micro operation fusion will do unlamination around the rename and instruction decode queue. And it turns out no one ever talks about that other than like Peter Cords. So, and Agner-Fogg, I guess. So yeah, those are the people that you should probably look at if you want to look deeper into this. Otherwise, just use this knowledge that I've given you to go make better code, because we have really, really, really slow code. That's all. It's so crazy. Yeah, it is crazy.
You write your thing out, or is it?
Yeah, overcurred. Yeah. All right, we're good. Fair enough, fair enough. I mean, if you're losing it, you're losing it.